Okay, well, hi everybody. Let's start. Thank you so much for coming. This is going to be a very fun workshop. My name is Brian Skinner. I'm one of the co-organizers. Most of the work was done by Alex Kamenev and local people who are not in the room right now, but we'll thank them later. This is going to be a fun, kind of playful workshop that is broadly dedicated to long-range interactions and strong disorder, and you'll see that explored from across condensed matter, including into biophysics and neuroscience, and we're all just going to try to have some fun. But of course, it's not exactly a coincidence that you see a lot of, Shklovsky disciples in the room, because to a large extent, this is kind of a chance to celebrate Boris's induction into the National Academy and get a lot of friends together in that sense. So the program is listed just outside the room. Unfortunately, we don't have printed ones for everyone, I don't think, but you can see it. Well, we have dinner today at 5:30. Any questions you can ask me or ask Alex or ask the administrative organizers who are just outside. That's Megan, who probably all have from. But otherwise, less talking from me, the better. Our first talk is Klaus Klitzing. He's going to kick us off with a 1-hour talk, and all the rest are 40 minutes. So whenever you're ready, please go ahead. Do we have or need a microphone? Should I get one for you? Oh, folks don't need it. Okay, well, let's see. If we need it, then I'll go find it.
Okay, wonderful. I have a lot of time now because it's just 5 minutes after 8. I have to until 10 o'clock. So. Oh, so thank you very much for the introduction, the invitation. Wonderful to be here. It's really interesting title: long-range interactions, strong disorder in physics and in life. And I asked myself, what's the reason that I'm here? I'm here because long-term interactions over large distances. Yesterday, I came here 7,000 miles just for this workshop here, and on the way I could also see finally the Oppenheimer film, to see the interaction between science and politics. It's been fantastic to see this, and this will play also a role in my talk in such way. So I can demonstrate that I have really long-term interaction already here with this university. I found in my files my first visit to the university 38 years ago. You can see here the announcement for the fourth pamphlet lecture. This was 1986. I gave 2 talks here. See here on October 15, October 16. And I was impressed by this program already at this time, because here the previous lectures, the first was P.W. Anderson, and then another Nobel Prize winner, Fowler. And the third one was Blaney from Oxford in England. I was a postdoc there and mainly a hero in electron spin resonance. I learned a lot of things there. So this was really fantastic speaker in this series. And my talk was not so bad. Perhaps I continued the series even today. We have the one black lectures here. And I saw here the list. So after my talk, Gellman was here, Braiding, Ehrman, Pounds, Paul. Fantastic program. And I think last month you had the last one. I saw here, for example, Horst Stürmer was here, Stephen Schuh, Kettle, Leggett, Berish, Grossberg, Teilinger, Dresselhaus, Geim. Fantastic. I think this is the most prestigious lecture series. I attend many of these such lectures, and I hope that most of you participate in this. So who heard my talk 38 years ago? Nobody. Oh, I'm happy, me. Because I spoke about application of the quantum Hall effect at this time. And I can use the same title to my talk 30 years old. But there are some new developments and some new application of the quantum Hall effect since 20th of May 2019, and really worldwide introduced by law. So I will speak a little bit about this topic. And the 16th of October, this was a talk I gave here, was exactly 1 year after the announcement of my Nobel Prize. I was quite busy at this time, but when I got this invitation, I said, okay, I should come here to this place. And to demonstrate that on 16th of October, I have here the modern type or the old type of emails. The 16th of October, Telegram doesn't exist anymore. And it said, "Dear Professor Klitzing, I have a pleasure to inform you that the Royal Swedish Academy of Science today has decided to award you the 85 Nobel Prize for Planck. So this was the 16th of October, 1985, and exactly 1 year later, I stayed here at this university to give a lecture about the application of the Planck model. So, you know, the Nobel Prize, so this is a document, the quantitative artifact, but I'm here not for the Nobel Prize, but for the focus of my lecture. As I've mentioned already, here you see new members, also Philip Kim, who is next speaker. They were elected for the National Academy of Science. Last week, there was a possibility to sign the book in Washington. So, congratulations. And I had interaction with both over a very long time. Yesterday, we spoke about it, but even longer than I remember. Before I got the Nobel Prize, we had already interactions. But I remember 30 years ago, 1993, we had a conference, Interaction Memory Field, and speaker was Jasman, McDonald. You can see all the people which are also here at this meeting. This is really an old boys club. Because if you look at the names, very, very few females. Also at this meeting here, I didn't see a female from here. So, and already at this time, we had very, very few females. So we have to do something against this, and welcome for the few females here in the audience. Be encouraged to work, make publicity for this field, yes. And the old boys should also do something against this discrimination. So this was a conference in '93, and 1 year later, we had also a conference here, a workshop organized by Klaus about compressible states of quantum artifacts. But you remember in 1994, and when you invite me, you send in a list of speakers, following participants have already agreed. And look at this list once more again, a lot of people which are here at this meeting. So very sure we will be here. Jim Einstein is announced, so McDonald here. So you see all these famous names here, which were already 30 years ago in this club related to quantum physics. Now, if you look at the homepage of ours, so this is our common interest, quantum Hall effect. And when I looked at the Wikipedia, at this time I discovered really that you had this 80th birthday. So congratulations, it was mentioned already some months ago already, but it's fantastic. I'm older than you. And you normally there's a birthday cake. I forgot to bring the name here, but I have a picture of my birthday cake. So this was a birthday cake. So this was my birthday cake. And this is in some way also the outline of my talk. See here, this will be an important part at the beginning of my talk. Here, this is our new measurement system, the SI-based units. And for the public, the most interesting part is that we have a new kilogram since the 20th of May 2019. So this kilogram is not anymore the prototype in Paris as a reference. There, I will speak about. And this is, for me, very important. The Klitzing constant, RK, H over E squared, time constant, elementary charge. And okay, quantum metrology will be a very important part of my talk. And I selected therefore title of my talk, Quantum Makes a Difference. Just adding to the classical world of quantum, then you get a Nobel Prize. So easy. I remember when I was a student, the Hall effect was a terrible phenomenon. I was happy to have within 20% accurate values for the K density of a material. There's so many corrections. You have a scattering correction, you have to adjust contacts. And so this was really a dirty effect for me all the time. And I never could expect that such fundamental phenomenon comes out if you add just the quantum to the Hall effect. So quantum is everywhere, and in principle, everyone who works in physics and basic science, modern science, is doing quantum physics. So it's nothing new for us in principle. But if you start to talk about quantum, normally you have to cite Feynman. And therefore, I have these two quotations here. There's plenty of room at bottom because it's nanoscience. Today we call this quantum devices or quantum sensors or something. Everything is quantum today. But if you work in nanoscience, everything is already quantum. And then if you work in the quantum computer area, then this citation is very modern today. Nature is a classic. And if you want to make the simulation of nature, you better make it quantum mechanical. This is an argument today for many applications to go into the direction of quantum simulation, quantum computer. Now I took this quotation from Feynman because I have a photo of his blackboard when he died in Caltech. And this final blackboard left by Feynman in 1988. What I cannot create, I do not understand. And the most interesting point is that to learn, we go down to the hall. At this time, he was confused how it works to the hall effect. That such a fundamental result comes out from the quantum Hall effect. Okay, but he didn't contribute too much to this field. But I will speak about the 2D Hall. And I will start with quantum metrology, a very small part of the activities in this field. The quantum revolution in metrology. So metrology, the science of measurements, some people mix it up with meteorology, so with climate change or so. So metrology is the science of measurement. And really, I'm happy that for my discovery 44 years ago, 40 years later, we have really very important impact on our international system of units. So I use this argument very often to make calculation for basic science. Sometimes it takes 50 years really to have breakthroughs in the applications. And this is the case for this discovery. This was really an unexpected discovery 44 years ago. And I am happy that just 5 years ago was really a breakthrough in one of the applications. So all non-scientists or scientists should know that all measurements in our universe can be traced back to the 7 base units: the meter, kilogram, second, ampere, Kelvin, mole, candela. These are the basis for all measurements, everything. And new definitions for 4 base units since the 20th of May 2019. So this is the revolution in metrology. And in Korea, they have even a stamp. So there was a stamp, and those announced that the mole, the Kelvin, the ampere, the kilogram, they have new definitions. And on 20th of May, there was a worldwide change in the measurement laws, because for international trade, it's necessary to have the same laws to go to these new definitions. Therefore, the international community agreed to have at this day worldwide this change. In our daily life, we don't see changes because there are only relatively small corrections which are not important in our daily life. And the analysis of this change, there was a lot of PR, there was newspapers, many about the kilogram, because everybody knows the kilogram. And the analysis said that about 2 billion people worldwide heard something about this revolution. 2 billion, 25% of the world population should have heard something. I can't believe, because when I discuss this even with physicists, some theoreticians say, okay, I don't care about it. It cannot be 25% of the world population which know everything. Therefore, I will repeat again something about our base units here. Even the New York Times, they had a coverage of these important meters, 26 meters of the International Committee of Base Measure. They are responsible for worldwide unification of measurement units. And the time was representatives of the meter convention voted anonymously to redefine 4 base units of measurements: kilogram, mole, the Kelvin, the ampere. Amongst them was Klaus and Klitzing front row taking a picture. And I discovered me. So, because I attend many conferences, but this was very special one. So I made such a photo that at the conference, everyone stood up and made a standing deviation for a decision they had made. It's unbelievable. These are the representatives from all over the world which had to vote for a new system of units. And this was really fantastic experience. So I have here slide about new definitions. So this is our only educational slide. Please remember this. If you have to give a lecture about our units, you should not say the kilogram is this piece of metal in Paris. This is wrong. So forget it. The Planck constant, H, this is the fixed value today, which is the basis for our kilogram. And the fixed value for the Planck constant will never change in the future. There will be never change in these numbers. So please keep in mind this number, which will forever be a fixed number, and on the basis of this fixed number, there are different ways to realize the kilogram. And really, Planck, since I'm a member of the Planck Society, and back at the Max Planck Institute, I had to make some calculation for Max Planck. Here, Planck constant was upgraded. It's not one. Already, since we celebrated his 80th birthday, I found some files about Max Planck's 80th birthday, and I tell you some story about Max Planck and his 80th birthday. This was in 1938 when he celebrated his 80th birthday, and Heisenberg was at this party also. And Heisenberg had the idea on Planck's 80th birthday, he should carry out a new position determination of Planck's constant and give him the new value as a birthday. This was the idea, and they had really ceremony at the 80th birthday of Max Planck, developing a new value for the Planck constant. Because Max Planck, he was fascinated by the constant, by the Planck constant. He discovered with the black body radiation, or he introduced the Planck constant, the Boltzmann constant. And he was more fascinated by this constant than by quantum theory. He didn't believe that photons were this modern aspects of quantum. He was, in his first publication, he had an extra chapter about fundamental constants and the importance of fundamental constants to use them as units for measurement system. This was the starting point of the Planck units, but unfortunately, the Planck units are not useful for practical applications. So therefore, that was the idea, and I have a picture of this 80th birthday. So this was the 80th birthday on the 23rd of April 1938. This was in the Hana House in Berlin. This is one of the conference centers of the Max Planck Society. You see here Max Planck. When I saw this picture, I saw that I forgot my dinner jacket for the night and the black tie, but I think the rules have changed in the time. And there was this party, and there was a dinner, and I have here really even the menu card from this. This is a correction by Max Planck. And okay, first, body radiation. This was the heater to prepare the meal for the dinner. And then here was the food matrix and fluids for turbulent flow tests and so on. A lot of jokes, the red wine was with huge events and all kinds of things. But more important was here the theater settle. So the theater performance, the position determination of Planck's constant. This was really announced as a piece of theater to determine the Planck constant with very high accuracy. And I have some pictures. You see here Werner Heisenberg, here is Peter Debye, Herbert Stewart. They made a presentation with some eigenmode noise. And in this way, they made several experiments, and then digit by digit, they constructed the Planck constant. And the final result was H was 6 points, you see, 6, 5, 4, 3, 2, 1, 0. So this was the gift, and then some person from the post office came and gave it by a telegram to Max Planck a new value for the Planck constant. So this was a theater, and I am sure that Max Planck was very happy to get finally very accurate value for this constant. So fixed value of the Planck constant. This replaces the kilogram per perfect pairs. So now we have to replace here this piece by Max Planck. He was elected in the Hall of Fame in Germany just 2 years ago. We have in Germany for all the important military people or politicians, and very few scientists are normally elected in this Hall of Fame in Germany. That is the Valhalla in Bavaria. And now Max Planck is there also in this ordinance purpose, because this constant was updated now with this new system of units. I will not speak about how you can realize from the Planck constant the mass. One way is the electronic kilogram. And this electronic kilogram, where you balance the force of a kilogram against the electrical force, you have to use the quantum voltage-Josephson effect, the quantum Hall effect, and by combining them, you get a one-to-one relation between the mass and the Planck constant. So this is one way today to realize, starting from the Planck constant, the mass. In former time, we used the kilogram to determine the Planck constant. Now they change the direction, fixing the Planck constant, and then have a realization of the mass. So please keep in mind, this is today the correct definition of the kilogram. And the same for the other three base units. Just summary, the Kelvin is not anymore the triple point, it's not a fixed number anymore. We have today the Boltzmann constant, a fixed value. And you can use all kinds of experiments to start from this value to realize temperature scale, from noise, from black body radiation. There's many experiments where you can start from the Planck, from the Boltzmann constant and can realize fixed points in the temperature scale. So this is the official definition. This we have to give up this fixed point of the triple point of water. It's not anymore a fixed number. The same for the Ampere. Originally it was force into wires. Today it's fixed number for the elementary charge. This value is fixed. All these values will never change the value anymore in the future. And also the mole has been changed. Originally it was connected to carbon isotopes, but today it's just a fixed number. The Avogadro constant is fixed by this number. So keep in mind these new definitions here. The velocity of light was already fixed in 1983. Fixed value for the velocity of light. This value realization, the base unit of meter. And this was the blueprint for this new development. We had already in 83, when we tried to measure the velocity of light, then the limitation was meter. And therefore they changed the direction, fixed the velocity of light, and the meter is today realized by the atomic clock and this fixed value of the velocity of light. So this is our new system. And this meeting in Paris was really a historical event. This was the most fascinating conference in my life. And I had the opportunity to speak at this audience. And it was so fascinating because if you know the situation, for example, in Europe, we have never agreement if you have a new decision by the European Parliament. There are always some countries who say, okay, no, because I get more money from the government. For example, but Hungary, they said, well, yes, we will vote for this. Normally, they want also to have more money. Or look at Turkey. They said, oh, yes, we want to change our system. And especially the United States, they were very happy about this change. I had here the representative from the United States. He was laughing because now he has not to go to Paris anymore to find out what a kilogram is. So you can do at home, yes, make America strong again. So, and all countries, the Russians, the Chinese, all countries agree. This was the only international conference where all countries agreed. I think it will never happen in the next 10 years.
Maybe
all countries. And therefore, in a certain way, quantum metrology united all countries. You have here books printed in Chinese, in English, the new international system of units. And mainly the focus on atomic clocks, using the quantum Hall, single electron pump, and so on. These are all quantum effects which are important for metrology. Sure, I have to focus on the quantum Hall effect, and I will tell you a little bit more about the quantum Hall effect. And if I give a talk about quantum Hall effect, I always like to show the first picture of the discovery of the quantum Hall effect, because everyone is laughing about this, because there's red wine here. Baguette and cheese, you see, it was in France. It was in the Nobel. It was the Nobel Prize discovery on the 5th of February 1980 at 2 o'clock in the morning in the Nobel. So this was a photo from 5 years later when I got the Nobel Prize. The journalists wanted to have a picture, so I had to sit down, and I don't remember. This may be the only change. I never had the white coat in my experiment. But the journalists wanted to have it. But all the other things are quite correct. So we had always at midnight meeting of all the scientists which were still working in the lab, and we had some cheese and baguette and red wine. You know, alcohol is forbidden, but in France, red wine is like water. It's it all. Yeah. Now, so some interaction with some wine and cheese is very important. So I will mention tonight we have a new location. You don't go to other rooms. No. Then we have perhaps the interaction also with some wine and cheese to discuss science. So this was the original notes in my notebook. Today in the museum in Germany, but at our institute we have also this picture, and this is the important equation: the Hall voltage H over E squared time constant divided by everyday charge times current. And this was the first time that this relation was just written down. The voltage proportional to current is a constant, which constant has natural constant H over E squared, which is about 25 kilohms. So this was a surprising result. I didn't believe that it works. And I wanted to know, because at this time everyone thought that disorder and localized states or give kind of corrections. But I found this in 1 hour, it works better than expected. So this was really an experimental discovery. All the ingredients were present at this time. The independent electron picture to analyze the two-dimensional system from an field were available. But first, the theoretician, I spoke to Anyon, and he told me they didn't know that you can measure directly the so-called rho XY component in the system by macroscopic quantity, by the voltage and by the current, which you can measure externally. So this was breakthrough in the experiment. So the first idea was new type of resistor, and I submitted it to official letters in May 1980, realization of this standard based on natural constant. You never saw a published paper with this title, but this is really today the most important application. This was never published, and I got then the realization of this done. The paper is not suitable for publication. And I could give an extra talk now about the history of this rejection and how it was published finally, also some months later, because I have now files of the referee reports. I know the referee from NIST United States, and I can show you at least some pictures. But the interesting point was rejection was on June 25th, and at this time I was at a conference and gave a post-deadline paper. And at this conference, one day before this negative decision, I presented a post-deadline paper about my discovery. And the Korean scientist, he contacted me at the conference dinner and said, this discovery will be won with Nobel Prize. This was the first time that I was confronted with this burden to be a potential Nobel Prize winner. It's dangerous to be so early. So we don't work for the Nobel Prize. You should wait until you are about 80, then you can. Okay, I have here just one picture, a triple report from Planck. He's one of the referees who was skeptical that this unknown person at the University of Würzburg, he didn't know Würzburg is East Germany or West Germany. And he had to write a triple report because he attended the conference where I gave a post-deadline paper. So the referee who rejected my paper came to a conference where I presented the new discovery. And then he wrote in his triple report on the 24th of June, the session I attended during the day, were mainly current electronics. The highlight of the former was a post-deadline paper, Klitzing, who reported on a new method from the fine structure constant from the all resistance of the damage, quite as elegant. I organized also an experiment. I showed the samples. He was surprised that I really exist and that the experiment could be really performed. He demonstrated this result, and he was enthusiastic. So we had some beer together in the evening. I explained everything, and he wrote then on 3 days later, I called Vic from Germany, one to PRL, this changes. So the only changes he recommended to change the title. The title, Realization of Resistance Standard, is not fancy enough for this. The new title, a new method for the high accuracy determination of the fine structure constant based on the Hall effect. Because if you look at the inverse fine structure constant, it's identical with H over E squared. You just change the name from H over E squared to fine structure constant, and therefore it looks much more interesting. today this type is wrong. We cannot determine from the quantum Hall effect to fine structure constant, because the quantum Hall effect, I will tell you, is a fixed number today, and the fine structure constant is not a fixed number. So this title is wrong. On the request of the referee, I changed the title, then it was published. Okay, you know the success story of the quantum Hall effect. The start in 1980. Here are the papers per year, and it's still increasing here. You see the first plateau after I got the Nobel Prize, and another plateau after the fractional quantum Hall effect. And then here, during the last 20 years, still a strong increase. One reason is graphene, because really graphene is such a wonderful two-dimensional system, and it boosted really also the research in the quantum Hall field. And you see here these names. When Black lectures, Sturm was here and Guy, Kim gave 17-year talk. So they boosted this field, and then the topology, Saul is holding Kostelitz. Again, today's quantum Hall effect is very often cited as the basis for topological insulators and so on. And I will concentrate on this small peak here, when the quantum Hall effect in metrology played an important role, we had an additional peak in the citations. I have here some picture of the impact of the original quantum Hall publication, and the color is the age of the publication. So the blue is the old-fashioned quantum Hall effect, and in yellow and green you see here the scale for the time. The yellow is 2020, and today topological insulator is a fancy field in related to quantum Hall physics. And you know, the topological insulator, sometimes it's shown as a ceramic plate with a gold ring that inside is insulator, and you can measure here zero resistance at the outside. So this is a picture of a topological insulator. But in reality, the insulator is not as insulating as expected. I mentioned this because he made a publication. Why is the biochemistry of the topological insulator so small? You remember the chairperson, and you publish this, and then copying and all kind of disorder plays an important role. So zeros are very often not reached at final temperature. So therefore, there is still a lot of physics behind it, and even today it's not easy to have a topological insulator which is really an insulator inside. And so this was already more than 10 years ago. It's still a modern topic, and I will not go into this field. I will concentrate on this small branch of quantum Hall physics. This is the metrology here. You see here metrology from Klitzing conclusion effect, international system with unit Planck constant, Kibble balance, Watt balance. These are the topics in this field. Now, if you want to do today quantum Hall effect, and we are doing this in the practice course for the students, the simplest way is really to use graphene. You can prepare this in the lab, just making contact, then magnetic field, then the Hall voltage, and then you can measure the quantum Hall effect. It's quite easy. And this is one demonstration of the quantum Hall effect. And you see here the red line is the Hall effect, up to 80 Tesla in pulse magnetic field, published already here 8 years ago. You go up with the Hall effect, like in the chapter, but then you stay here up to 80 Tesla at a value of 12,906.4 oops. This is really impressive, but this is a special situation. This is graphene on silicon carbide, and silicon carbide has some special properties. They have a reservoir of gas at the interface. They can feed electrons into the system, so you can stabilize the plateau at the so-called Planck factor 2. So this is different from most of the other systems where we have normally a constant number of carriers in the two-dimensional system. Here we have a big reservoir at the interface, silicon carbide. But this material is today perhaps or will be in the future the interesting material for applications. Now, what are the experimental tests? I will just start as an experimentalist with the test. I discovered this on the silicon field effect on the uniform at the interface two-dimensional system. But the gold standard today normally is still gallium arsenide heterostructure. In both of these systems, you can, like in graphene, form a two-dimensional system. And the first test where we need to compare different materials, silicon against gallium arsenide. Already in 1999, Arden, he found out that this sample has the same proton value with about 10 digits. So this is the experimental fact. Then has done this with different samples from gallium arsenide, epitaxial graphene against gallium arsenide, exfoliated graphene, even the so-called fractional quantum Hall effect, or the quantum anomalous Hall effect. All of them within the experimental accuracy gives the same value for the quantized Hall effect. This is an experimental effect. No significant difference at the level of 1 part of 10 to 10. This effect, maybe the gravitation makes a correction, that the expansion of the universe makes a correction, but experimentally, all of these show on Earth, in all countries, the same value. So this is very useful for practical application. Now, the best material is still gallium arsenide and epitaxial graphene, on silicon carbide. And the reason is that this will win because you can run this material at much higher currents, at much higher temperatures. So I have here a graph for the temperature range, magnetic field range, and the current from the sample, where you can have an accuracy of this plateau with 9 digits. And these graphene and silicon carbide is this area, and gallium arsenide is relatively small magnetic field range. So with graphene and silicon carbide, you can go up to 500 microamps with a sample. Huge voltage still works. You can go up to 10 Kelvin, and magnetic field of some Teslas normally run at 7, 8 Teslas. The system gives you very stable quantum Hall. In gallium arsenide, this is a show curve from one of my students where at low temperature. So this today, the quantum Hall effect result for the gallium arsenide. We see the classical Hall effect, but then a large number of steps, and then here magnetic field rate. You see that the Zeeman gap and the Nano gap, you don't see any differences there. The energy gap size is not important because in this case, you have only fixed number of electrons, and the degeneracy of each level is the same. Therefore, as long as you have no overlap between these energy levels, you see 1/b series of all these structures. You cannot get any information about the difference in the energy gap. Only if you go to higher temperatures, you will see that this disappears. The Zeeman gap was much smaller, more than order of smaller than the Nano. But this is a typical example that we keep the K density constant in these systems, and therefore we have these equidistant or 1/b equidistant series. Now we can have even quantum Hall effect today, not only with 25 kilo ohm. Here is 1 mech ohm. There's a quantum Hall factor 1 mech ohm. Here is half mech ohm. Today you can arrange all kinds of resistors because the industry they want normally 100 ohm, kilo ohm, 10 kilo ohm, or mech ohm, and there are modern arrays which are used in quantum Hall physics. You have the combination of quantum Hall devices, and today we can have with these devices, which you can put in parallel and in series such devices, all values between 100 ohm and 10 mech ohms. You have to just combine them to optimize it very close to these decimal values. And you may be surprised that you can combine with high precision such devices. This could be an extra talk. You have normally with these leads, you have some contact resistors or some wire resistors. And at the level 10 to minus 9 or so, you have to worry about all kinds of contact resistance. But there's a trick in quantum Hall devices. If you have a bypass, if you combine the source, for example, with some edge of the sample, if there is some voltage drop in the leads, then you have automatically a current, an additional current, which corrects for these additional resistors in an exponential way. Normally, we have 3 additional contacts. So if you have 1 ohm contact resistance X or Y resistor, then relative to the quantum ohm from 25 kilo ohm, you can exponentially reduce this error to 10 to the minus 12 if you have 3 extra leads on one side of the sample. So there are some tricks to have really a two-terminal resistor, which is very accurate in quantum Hall physics. You can have just two-terminal resistor between source and drain with some extra correcting leads, which gives you the correct value, even if the wire has a finite value. So this is interesting development. Therefore, you can build up these arrays and you can keep the accuracy of this. But I will not speak this. But so what is the simplest explanation? I give still some introduction. Normally, you have this picture in mind. If this is a sample, then the electron-magnetic field they make these cyclone orbits, and the quantum uncertainty says that each of these orbits uses a certain area. Each orbit needs an area, the area of one flux quantum. This is quantum mechanics. Normally in physics, you learn that in phase space, in momentum and in real space, we have this uncertainty. We need a certain volume of a state. But here in real space, if you transform it so magnetically, each orbit needs a certain area in the sample, the area of one flux quantum. And then the quantum Hall is closely packed these Bohr orbits in the simple picture. And then you cannot jump from occupied to an empty state. You have this incompressible state. This is the ingredient of the quantum Hall. It's always dangerous to use these pictures. You know already the Bohr orbits is a dangerous picture, but I think it's most common and it's useful still to speak about Bohr orbits. And very often quantum Hall physics, we have these pictures of these cyclone orbits. But in a single electron picture, you have different representations. And normally we use this picture. We have this energy scale with different quantized level for two-dimensional system magnetic fields, these Landau levels. And if this is fully occupied and this is empty, then we have the quantum Hall field. And in a simple picture, it's just a single electron picture, the generator for each Landau level is this, and then put it in the classical Hall field, you immediately get this result that voltage is HOE squared times 5 for a fully occupied energy level. No scattering from occupied to unoccupied states. So this is a very, very simple picture, but all pictures are wrong in quantum physics, but it's sometimes useful. So I mentioned that you normally can use different representations. This is one of the representations. This is the so-called von Neumann lattice, where you have these areas of one flux quantum in the sample. But we have other representations. Theoreticians prefer sometimes this symmetric gauge that we have angular momentum as a quantum number. I like the Landau gauge, where this looks already like a device where we have the current flow through a Hall device, and we have the Hall voltage in this field. And it's very useful to use this gauge for in the single electron picture, where we have the center coordinate here as a quantum number, and then we have plane wave in the other direction. So this is very useful and it's very interesting. Okay, go back, let's see. That this center coordinate is directly related to the K value of the plane wave in this direction. This will play a role in one of the next pictures. Now, the question whether why this quantum Hall effect works was really mentioned as an open problem in mathematical physics. But still, in 1999, there was a platform, and they asked, formulate a theory of the integer quantum Hall effect, which explains the quantization of the Hall connect, so that it applies for interacting electrons in the terminal limit. This was declared as one of the 10 most important questions in mathematical physics in 1999. And it took 15 years before the answer was published. So this was a publication of collection of significant problems. And this was communication in mathematical physics, published by Hastings from Microsoft Research Station Q and Mikhailakis from the Institute for Quantum Information in Caltech. And they published in the paper the quantization of Hall conductors for interacting electron conductors. We prove without any averaging assumption that the Hall conductor ground set is quantized in integer multiples of E squared over H. So this is the argument which is used today that the quantum Hall effect is really h/e². I'm still confused because there are publications also which predict some corrections. And I found quantum electrodynamic correction for the quantum Hall effect, published in 2003. Quantum Hall effect in quantum electrodynamics, a weak dependence of the universal complexity constant on the magnetic field strength. And in this paper was given that this quantum Hall effect is not h/e², it's not this one, it's a small correction. You see mainly the correction is a cyclone energy in relative to mc² for an electron. This is a very small correction. If you calculate this for the electrons, the correction is 5 times 10 to minus 21 for an electron mass and 10 Tesla. So, but to me, it's still an open question. Do we have fundamental corrections or not? I spoke about Halperin. He said, okay, that's wrong. Here's some general arguments, it shouldn't work. But I could not identify really the errors of these pictures. There are even publications that gravitational potential plays a role, but this has been proven also that the wrong arguments. So I'm still confused. I contacted Opinion, asked them, can we do some experiment? You know, in graphene, perhaps we can go with mass to very small values. If ME is massless, perhaps we can reach the area of correction. But he wrote me back, the mass in the formula is 1 to 3 electron. So that's the graphene correction is the same. So it's not worth to do experiment to find out whether we can see some correction. But it would be, or I ignore this, it's just 10 minutes before 9 before I start of the talk. Okay, so for practical application, we always use this argument with experimental uncertainty. This is really the correct expression. So the argument, main ingredients of theory, you need a gapped Hamiltonian. This was the ingredient for the theory. This is also argument by Saulus and so on. And so the argument is that we have here a gap, but we have not this order. We have not the edge. We have not finite Hall voltage. We have not included in this picture any correlation. And so the assumption that you have a real gap is not fulfilled. Boris, you were interested in long range fluctuation already. If it's a sample area, you have always some impurity, some disorder. You have fluctuation which can be much bigger than the gap of the cyclone energy. So we have already this picture that we have broadened random levels which may even overlap. And therefore, there is no gap. We measured the density of states in this gap. This was one of our publication, experimental density of state in the gap. This was here the result. And I remember Boris was interested in this publication about density of states by Dieter Weiss. And he wrote me at this time a letter. Dear Professor Klitzing, we were the last authors of this paper. Normally the first one which have done the work, they are ignored the last one. So I got a letter from Boris, and dear Professor Klitzing, I would be grateful for reprint of the paper density of state to the energy system, and you still the address so to the Leningrad. This was almost 40 years ago that you wrote this text. Always handwritten, so it's I don't know whether you have
KGB check.
or so.
And KGB check.
So I have many of your letters, so these are letters. They explain all the critical exponents and all kinds of things, and we had really very fruitful cooperation in this year.
Oh.
Now, even if you have no disorder, so if we have really an ideal sample, we have states in the gap if we have a finite sample, because the Lambda levels go up in energy at the boundary of the sample. So we have not really an energy gap. So the argument for the theoretician that we have only on the torus perhaps, that we have no states in the energy gap is not fulfilled in the real experiment. We have already, at least at the boundary, we have these states. And this is another activity of Boris to discuss these so-called edges in the quantum Hall system. And I mentioned already that we have this relation between the center coordinate, kx, and here's energy. So if you look at the Landau band, it looks identical like a one-dimensional 3-electron system. is the E over kx one-dimensional system. We have here finite E over dk. We have here finite group velocity as the boundary. So in introduction in solid state physics, perhaps sometimes we have to calculate what is the one-dimensional current of a one-dimensional system. Normally we discuss the change in the electrochemical potential if you apply the voltage, and if you have no backscattering here, then you can integrate for all these states, and then this has been done, for example, in many publications, where the density of states and the group velocity cancel, and you have really the relation for one-dimensional channel. Here, you can realize this also in this so-called point context. You have the current is exactly E square over H. You have this quantization for a one-dimensional channel. Therefore, quantum Hall effect and ballistic transport, ballistic means you have no backscattering, this have some connection. And each of these dispersion curves looks identical to another level with a boundary. So the dispersion is quite different here. And the problem is in quantum Hall physics, this dispersion here in the occupied states may change if you have non-equilibrium. So normally in material, you have a fixed dispersion curve, you're not changing it. But in a quantum Hall device, in the inner part, you can have some tilting of these levels and so on. So you can see nicely the quantization for these one-dimensional channels. So there is some similarity between ballistic transport in one-dimensional devices and quantum Hall effect. And these are the two limits of the discussion of a quantum Hall device. So if you have a quantum Hall device, I showed you this place, a picture. If you say non-equilibrium, if you put a current, then we have a Hall voltage between this side and this side. So we have difference in the electrochemical potential of this side to this side. And you can discuss this just by adding some extra electrons on this side, removing some of this side. You're just changing the chemical potential to just the occupation of the level, not the electrostatic potential. For the same difference in the Hall voltage from this side to this side, you can have also this picture. That you tilt the number of levels. And if you calculate this, then you have here a real edge current. This is a Büttiger formalism, mainly where you have only the edges. But here you have bulk current, you have a tilted system. Even these occupied state, they have a velocity. And therefore, this is one extreme that you have bulk current, edge current, but the final result for quantum Hall is the same. Because only the boundary, this difference plays a role as long as you have no backscattering. So, a determination of the current distribution requires information about the Hall field in relation of all states below the Fermi energy, which require a net drift velocity because of the Hall field. So this is the question you have really to solve this, and this is for each sample different because you have disorder, we have fluctuations. This is very complicated what happens inside the sample, but only the boundary potential plays a role. So then this is one problem. Here in this picture, you have an abrupt change in the Kerr density. Kerr density is not a step-like function. And I have to mention this famous publication, which plays an important role in our field, the electrostatics of the edge channel. So we have not the Kerr density, which goes like jumps. You have to include the screening. And then we have this picture, which is very famous in our field, about compressible and incompressible stripes. So the yellow one are really where Fermi energy is in the energy gap. So we have here the situation that we have two levels fully occupied. Here we have one level fully occupied, and the other one you have a continuous change of the Kerr density. These are compressible stripes where here states are at the Fermi energy. Here are gaps, here states at the Fermi energy. You can call these metallic stripes, and the other one incompressible stripes. So you can use this picture as a boundary of the sample. So the colored one are these quantum Hall situation where the Fermi energy is a gap here. We have three levels occupied. So I use by 3 Then at boundary, you go slowly to zero. This is an area of order of micrometer. And then you start somewhere with Filling factor 2, somewhere with Filling factor 1, but it becomes always smaller things because the potential, combining potential becomes steeper. And therefore, you have such a situation at the boundary. And I know when this picture was developed, many people believe, okay, we have here these nice metallic stripes, which is exactly the number of the filling factor. This looks like a one-dimensional system, so we can use the argument of the ballistic wires. But this is a one picture. The non-equilibrium current does not flow through these metallic stripes at the edge. This is a one picture. So you can find many publications which gives you this one picture. Fortunately, many groups are now doing these measurements which we have done more than 20 years ago. Where do the electrons go? And this was just Nature Materials, some comment about the recent publication of Katja Novak, identifying the current path even in the quantum anomalous level. And we give a proof of existence that current will flow through the wire. In contrast to the common belief that current will flow only at the edges, the result shows that there's current passing through the wire, even of topological insulator. Very similar picture to the quantum Hall effect. And today, the current, the external current, is not flowing in these so-called compressible stripes, these so-called metallic stripes. You learn always everything happens at the Fermi surface. Now the Hall current flows in the incompressible region, where we have a difference in the electrochemical potential across the incompressible. I will come to this because this is really one error which is in the literature now for more than 20 years, and I'm fighting a little bit because some famous physicists have published papers, edge currents in quantum Hall system, which is confusing. Today, the sketch for quantum Hall device, for example, is 3 factor 2.5. 2.5 means in the inner part of the circle, we have two fully occupied and one half occupied. But at the boundary, we're reducing the Kerr density. So we're going here in the situation of Planck factor 2, here in the Planck factor 1. In between, we have these compressible stripes. And these light blue areas are the areas where the current is flowing. Already, we have equilibration current because we have here difference in the electrostatic potential. These states have a finite k variable, dE over dk. So we have already these arrows indicate the equilibrium current in the device. So one in one direction, the other in the other direction. This is a normal picture which can use the classical picture of skipping ball with or E over V motion diamagnetic current that's boundary. These are these currents. But if you have non-equilibrium, if you have a finite Hall voltage, so you have a voltage between this edge and between this edge. The question is, where is this additional Hall voltage dropping? And this additional Hall voltage drops in the region where you have the smallest sigma xx. If you think about the corbinal device between an outer ring and inner ring, if you want to put a current from this side to this side, you are blocking with these incompressible regions, these regions, a current, because these regions are really the situation of quantum Hall physics where we have sigma xx equal to 0. So the Hall voltage drops at the region where you have the widest incompressible stripe. And the result is at this point, and at this point, you have the big voltage drop of the Hall voltage. So the Hall voltage drops across the widest strips in strip. And the extra current flows in this region. And if you analyze it finally, you have some extra current this and in this part of the sample. Normally, if you go then to Planck factor integer, then these move together, and then the whole inner part is the main piece. So the injected current flows in the innermost incompressible stripe. And if you have a higher current, it looks like a PN junction in the inverse in the forward bias. Here, you can have finally, let's break down tunneling from occupied to empty states. So it's like a Esaki diode. You have your forward bias diode where you can inject currents. This has been measured experimentally. All this potential distribution I discussed before has been measured. And in this range, you can see even the cyclone emission because you inject the electron, you combine, and Japanese group have then looked at the emission of cyclone radiation. At the one edge, you see nicely the emission because you're injecting electrons in the background region. In this region, you are tunneling, and if you include spin, you make a spin flip normally in the stunning process, and you dynamically polarize nuclei. And also, this has been discussed. Here is a dynamic nuclear polarization measured, and at the boundary, if you have 3 factor 1.1, then you see at the boundary even 1.05. Maybe at the boundary, here some dynamic polarization of nuclear space. If you go to the integer, then the whole inner part is incompressible, then the whole inner part of the sample shows this dynamic nuclear spin polarization. And we have measured really the plateaus. So look for different sample widths. Want to see what is the contribution of the edge, what is the contribution of the bulb. The dark, the black area is a plateau as a function of filling factor, P2 and 1 and 1.9. If you increase the voltage, then you see there is some different changes. Here is the filling factor 2. And if you go from 7 micrometer to 40 micrometer, you see that maybe this part raises, the other part remains constant. Because this part is the left part, is the edge part, and the edge incompressed stripe remains the same independent of the width of the sample. But the inner part make more contribution due to this or due to localized state to stabilize the quantum Hall. So this is here the final picture of a plateau. If you have a plateau quantum Hall effect, normally in the right side, the higher magnetic field range, we have bulb-dominated plateau stabilization. On the left side, the edge which contributes to stabilization of the quantum Hall. So, important aspect of the quantum Hall device, the electrochemical potential of all compressible electron areas must be known. Difference in the electrochemical potential across incompressible regions lead to the dissipation of this Hall currents. Perhaps I will make a simple exercise, which is confirmed by experiments. But I will ask you this question: if you have a device, this is a device we have here, one contact, here contact. So the color is the potential which I apply at this device. So the blue potential is the red potential. And I will ask you the question: if the magnetic field in such a way that the skipping organ is anti-clockwise, how is the current flowing in such a device? So I have here put the so-called point contact, which means that we feed in only filling factor 1 by this contact, but already ohmic contacts, due to work function difference, very often they have the properties of this point contact because we have a reduction of the carrier density in front of the contact. So there's very big danger that if you believe a contact is a big reservoir, it's not really a reservoir. We have to know exactly what is the difference in work function between the different materials. Do we have a small depletion in the front of the contact and so on? But let's discuss this picture. I told you important is to find out the electrical potential in the sample. If you're anti-clockwise, then this side here is an exponential line, this red line is compressive line. But here from this contact, we go around this edge, then this compressive start and come to this to this contact. And then mixing there, this different potential, and I have this pink color, and out of this reservoir, then two pink compressible potential come in and enter finally this red contact. So we have energy dissipation at this point, the different potential comes together. At this point, the different potential comes together. And if you analyze this for the other magnetic field direction, the potential landscape looks quite different. We have clockwise, and clockwise means the blue potential goes up to this way, and the red potential in this way goes up to this contact and comes back here and mixes in here. So this is simple, just looking how the compressible stripes enters the sample, the electrochemical potential. And then we know if there is a difference between the across an incompressible region, they have extra current flow. So the current flows this way first and then goes down. In this case, much more difficult. Current flows here, enters this contact, and then goes to the bulb bed. And this potential landscape that we measured, we have done this with a single electron transistor on top. Today, there are more convincing experiments with a squid where you can really, like Biot-Savart, measure the magnetic field produced by the current. So this is the correct picture. And you see, just changing magnetic field, you have quite different potential in your sample. For example, this contact switches between two different potentials. You have some mood change of contact potentials just by this so-called edge current. Current distribution in quantum Hall field is complicated and different for each sample. The quantum Hall resistance is not influenced by the current distribution as long as the incompressible region blocks the backstepping, which means it needs the sigma xx equal to 0 through the whole sample. Now, in principle, I have to this title, quantum makes the difference, more or less another talk about not the positive aspects where quantum metrology united our world. I just mentioned that I think this quantum initiative in 2018, where it was mentioned that it was national security of the United States, we need this big project. And 2 years ago, there was even the national security memorandum on what the United States leadership in quantum computing by mitigating risk to a cryptographic system. In Europe, we have this very big flagship program, $1 billion program, quantum computation, quantum technology, and quantum becomes political. And for me, it's really disturbing science. If you look, the global efforts last year, 38 billion was spent, and about 50% in China. This made this confrontation now, which comes up and disturbs the cooperation in science. And you know, all these countries have billion-dollar projects just in quantum science and technology. Next year, we will have the World Year of Quantum Science and Technology. There will be another boost in this field. And I'm fighting a little bit against this hype. The fear is that the application of the Shor algorithm will be a risk for the security. But in the meantime, I learned a lot of things. I had recently a conference where really Google, Microsoft, IBM, Amazon, all of them came together. And they told us the problems with quantum computation to scale up. And this publication, the Chinese publication, Braiding the 2048 LSA code with 372 qubits. A lot of scientists say this is a wrong paper, but if this number appears and somebody predicts I can build a quantum computer and then I can crack the codes, so there are other publications how to factor the in 8 hours with 20 million noisy qubits, because all qubits are noisy. We have always to distinguish between physical and logical qubits. And I learned you need millions of qubits to have a really working quantum computer. And you cannot scale up the present technology to millions. If the transistor warms up, you have to tune each interaction between each qubit again to optimize it. This is exponentially difficult. And I'm very skeptical. We should not use this argument, the security argument, really to have this competition. And when can we expect a useful quantum computer? I believe now, will we ever have a quantum computer? You'll know, like Yakanov very well. He is saying, I asked ChatGPT. Many technical challenges they must be overcome before quantum can escape up to the point where they can solve useful problems. And up to now, there's no useful problem which has been solved. At other time they claimed that they will optimize the classical computer, supercomputer. You can do it better. And you need always a supercomputer to feed in a quantum computer. And I don't know how you want to crack the code where you have to put all the numbers of the prime numbers with a million of digits. It's a lot of work to feed a quantum computer. So the next talk will be clever, but because the two-dimensional system, they may have some new, the Anyons, their publication Braiding of non-Abelian Anyons, and Anyon Braiding in Graphene quantum fault interference. This is next talk. See you guys there? I'm waiting for your talk. Because this is really one of the most fundamental questions, the most interesting question for me in two-dimensional physics. This is really a new quality. And if somebody can convince me that this works, I look forward for your talk. It will be fantastic. It's a fantastic area. So, I think this is really a science, one of the most interesting questions for me. And hopefully in my life, I will see convincing experiments, and I look forward to this. So, the future is quantum, it remains quantum. Max Planck didn't believe in quantum physics, and Wall has some applications. Quantum metrology is only a small part, and I covered this one. This is still an interesting field and can grow great.
Okay, I'm somewhat inclined to keep the questions short so we can have more time to mill around and chat outside, but there's some time for questions if anyone has.
I can encourage questions. We will get the first four, we get the card with numbers to remember the base units. You see here all these fixed numbers which will never change in the star. And then due to H and E, then the Newton constant, the fixed constant, and also fixed numbers.
Okay,
So
okay.
you should remember.
Given the prize on the table, I'm gonna prioritize students. Prioritize students getting a prize. Any students want to ask a question and win a prize? Okay, yes, please, over here.
I just want to know, I did not figure out the reason why the current was going in opposite directions, in that sample.
Yeah, we have to look at the electrochemical potentials. How is the electrochemical, and you can feed in from a contact low to the upper part of the sample due to this metallic stripe at the boundary.
That makes sense, but why would it come down as well?
This is not definitely discuss this later. Yeah. Everything. So, this is the point picture. So from magnetic direction, you know in which direction the electrochemical potential is driven. You have here the red potential, yeah, this was the interesting part. Here there's a blue counterclockwise. You go here this, and then you go up. Right. And from this, all counterclockwise, this red one goes also up. And you have some different electrical potential, then the current flows there.
Yes, that makes sense.
So this is some non-local current flowing. You always believe something should happen here. No, some other places. So in Van Hall physics, you can see potential distribution in the sample where you don't expect some signals. Yeah.
Okay, now I'm willing to go to non-students. Yeah, no, go
Sometimes you
Okay, you get cut.
you have this picture of the density of localized and delocalized states in gallium arsenide. What does that look like? Because the graphene devices are much cleaner, right? Like, is
Yeah,
it
but,
still,
But
is it
just
similar
if you have
to-
potential fluctuation, you have hills and lakes in your potential, and you're moving on equipotential lines. So these are our localized states if you have long range potential fluctuation. Only at the percolation path you can go through the sample. So therefore you split off from the ideal nano level states, which are in the classical picture just go around the lake or around the hill.
So, and you're saying this is still, in your view, the right
Yes,
answer?
in all samples, even graphene, you have also somewhere some impurities.
Okay, maybe a couple more. I'm trying to remember who had their hand up.
Oh my
Misha,
God.
Ray, Alan, all that. Okay, other questions? All right, go ahead.
So candela is like luminosity, right?
Okay, this is
So
stupid. No,
why is it?
technology is for application. And the chemists want to have the mole, the optics, they want to have some calibrations. They are not useful from the physical scientific point of view.
Yeah, okay. So
That's just practical,
Fica forget
the
it.
practical line. Yes.
but it can be defined in terms of other base units, right? So watts per meter squared.
Yeah. Okay, but you still introduce spectral sensitivity of the eye, so that's
Okay.
practical.
Okay, well, let's, okay, one more.
Oh, no.
So, do I get a card?
You get two if you don't ask a question because I cannot answer.
Okay, so you talked about voltage drops in quantum Hall systems.
Electrochemical potential drops
Yeah,
for the external current.
right. And so we're used to in metals, the notion of even when a current is flowing, there's a local electrochemical potential that you can define everywhere in the system. Do you think that's always true in typical quantum Hall devices?
If you know the difference in electrochemical potential, you have a non-equilibrium current, it's my picture.
But if you're talking about at some particular position and you don't measure is there a well-defined electrochemical potential there when a current is flowing?
Normally, you determine externally the electrochemical potential.
If you measure it, you change it, right?
Yeah. So for me, the electrochemical potential is given by the battery, yes. And then you have an equilibrium in the whole sample, the same electrochemical potential, you have to adjust the electrostatic potential, you have the same electrochemical potential. Yeah.
Okay, we'll talk about it.
Yeah, yeah.
Mill around.
From dinner on, yes.
Okay, well, let's thank the speaker one more time. Right now, we're resuming 30 minutes to still.
We just ended our term, I think.
Yeah.
If you want, and actually, there's time for you to change it if you want. Yeah. You're thinking yeah.
Oh, yeah, the Anyon Center.
Yeah, I see.
Annex building, they have all the. They have all the. It's already built. When I was there. A lot of they built them, but they were empty, so.
Oh, yeah, it's that. This is, maybe.
It's amazing.
Yeah, but actually,
Different,
the thing is that they, I think at the time they were thinking of getting more. And also, sorry, so that was very new, like talking Thailand and very good. Look at all that actually. Probably if you want to give a.
Yeah, so they're not set up to.
And then, it's not. But now, we was even do renovations, don't stress too much. Now they hire for the now. Also use lots of power consumption. Yeah, sorry, higher biology. Yeah, so
I see.
you can talk to me, but I won't be here tomorrow.
It's a beautiful.
But scenario, someone will let you.
They have. Loading, it's like, several times. Which we're just sitting there, like it's not like we don't. You know, it's scanning some sort. Yeah. You know. Why not?
Yeah.
I mean, now you. This would be nice.
Oh,
I'm
so
sorry, I thought you would definitely. So, Hamburg,
yeah, that was good. Actually, I've never been there.
okay, I got all mixed up. So, Wiesendanger and, I know, the scanning guy there is,
No,
no.
he's gone, actually. He's retired.
He's not that much older than me.
No, I think we're talking about.
Who's the scanning guy at Hamburg? Because you said.
Yeah.
It's like my physical chemist.
The SCM guy.
There were two directors.
University of Hamburg.
Oh,
Yeah.
Roland.
Yeah.
Roland, yeah. Yeah.
Retired.
Yeah, no. Yeah.
Scared me for a second.
No, I think he's retiring a few years.
Well, they have the German
Yeah.
system. 65. Yeah. I see.
Maybe
So
they-
you're at the University of Hamburg, right?
Yeah, I will be a free.
Okay.
Bye. We can change the mind still. 65, we just approach it very quickly. Sorry. I think that it's like 2 years away, but you don't use it.
Now it's more like 70.
Oh, are they upping it?
It's not up, yeah.
They don't have young people.
You can delay a little bit.
They have now the official rule that you can delay the 70s or that.
Well, yeah, they almost automatically
I
do
see.
68,
Okay.
but they
Yeah, I
anticipate
see.
a little later,
Yeah.
further,
I think, yeah.
because I think people just live longer
Right, yeah.
these
yeah.
days,
And
and
they're not making babies. Either.
That's right. That's
So-
right.
That's the problem.
Yeah.
the problem for all developed countries.
Yeah.
I mean, especially Korea. I think the
0.8, 0.8.
0.7.
0.7.
No, I think China is still
better than.
So two generations.
Korea is the
Oh, yeah,
Korea is. What's going on there?
House price.
The North is gonna win by default.
Yeah,
It's
yeah,
not gonna be.
that's what I think.
Not going to keep that number. in the future,
Yeah, but
right?
we'll see that.
When
I
it
think,
really goes down, it will
yeah,
come back up.
yeah, but that's.
It's just,
We did this one, two generation, basically, or almost 16.
it's astonishing with the, all the famines and the
Yeah.
prison camp,
Yeah.
that the North is outbreeding the South is.
Yeah.
it's-
Well, okay, so I think that the housing price and all these things, and that. Hey, how are you? Good to see you.
Nice to see you again.
Yeah.
Oh, hey, Ray.
Hi.
Nice to see you. We met in like in one of the workshop in Lushan many years ago.
Okay.
But I forgot.
Yeah, yeah,
Oh,
yeah.
hi, nice to see you.
I see you.
Oh, yeah. How was your flight?
Was,
You were here yesterday?
No, I took
Wow.
the morning. 6 a.m. flight. I think.
Wow.
I'm getting rid of
Oh.
it.
Then you drank some coffee, I guess.
Yeah, I should.
So, when's a good time for you to?
It's- I thought maybe you were still feeling it.
No, today is climate change.
Okay.
And I'm on the road just trying to find somebody to talk to.
Yeah, I recovered your results. Yeah, yeah.
Good to see you again.
Okay, so let's continue. You may have noticed that the morning session is sort of quantum Hall themed, and now we're going to continue with Phil Kim Harvard, who's going to tell us about Anyon braiding. Please go ahead.
Thank you. Right. Thank you very much for inviting me again to the Minnesota. I think somehow the Zoom is very fun. It's still like the second home. Many times I came here, people talk here in this room. So when I was invited again, that I thought, wow. It didn't take the Canadian seconds. Oh, yes. I didn't really carefully, but perhaps it's somewhere behind it. I didn't know that this was not just kind of good workshops that we can all get around, but we might do some special events, because during this Klaus talk, I just kind of, no, I probably missed something. And quickly, Google go to the Wikipedia and find that this is the area for the boys. Congratulations for this kind of great lifelong career, and nurtures not only great science, but also nurtures many scientists, including myself. I think I learned a great deal out of this all many years of interaction with boys, or others in the room. And so I'm going to also, it seems like there's a big shoe that I have to kind of dig in there, especially after Klaus talking this morning. Unfortunately, I'm going to disappoint you that there's yet a lot of the progress has been should be made. But at least I feel like that there has been meaningful steps have been made in the community, and this is probably a good time to sharing about the development in the field. So I'm going to tell you about this Anyon braiding graphene quantum interferometer. Of course, this one really kind of built on to the quantum physics that Klaus actually mentioned. And we start with the acknowledgement of this, the people who actually did the work. Major part of what basically is based on this two archive paper is done by the Tom, who has been now the collaborator with James, and these two guys actually put their other efforts on it. Two work that I'm going to present. Earlier work is basically initiated by the Yuval Roman, who is now in the Weizmann, and he himself is leading this group to come up with a very interesting meeting today as well. And we have a strong collaboration with the Anyon group, and also very strong theory support with the bird and in collaboration with the unit. And obviously that many of the graphene sample to reach the high quality, the heterostructures, the encapsulation with high quality boron nitride is important. That is supplied by our LIMS Japan. Okay, so because this talk is kind of talk about this Anyon braiding, maybe I should probably introduce briefly the Anyons into the talk, and obviously there are more people that much more there's much more authority than I have to describe this one. But concept of Anyon comes from the thinking about exchange statistics of the quantum particles. we have the indistinguishable particles in quantum mechanics, especially in the higher dimensions, then there is because of this exchange is symmetric, that there's only the two kind of quantum particle can have that in terms of the quantum statistics, meaning that when you just exchange these particle indexes, where the wave function of this particle contains a positive or negative sign, which actually kind of categorize the quantum particle into the bosons and the fermion. This is kind of well-known. In fact, we all teach this in the introductory quantum mechanics class. Now, this story can be tweaked, especially in the lower dimension, 2 dimensions in particular. In 2 dimension, in some sense, when you just kind of exchange this particle, this exchange operation is confined in 2D, where that topologically the winding number is well defined the topological embedding, provide us in some sense the other possibility. In principle, one can get the different kind of the fundamental particle, which actually has a different quantum statistics. That idea first kind of be conceived by a few mathematicians. Eventually, they wrote this very seminar paper in the 80s. Tells us that indeed, by exchanging this the particle in the 2D, there's a possibility you get this phase is not defined not only positive or negative, but the space can be some kind of well-defined numbers in the sum of the rational numbers you can get into the structures there. And in particular, that as soon as the quantum Mode effect is discovered, especially fractional quantum Mode effect, when you just write down this Raphine wave functions, that clearly that the particle of the Raphine wave function provide this kind of realization of the limits. And furthermore, in principle, that if the ground state is a degenerate state, there's a possibility that even just kind of after braiding, we may actually map this one wave function to another one into in the ground state kind of manifold, which allows us to even just this braiding operation, the 2D can result into this Anyon, which is kind of non-abelian characteristic. And this has been kind of one of the interesting and exciting discussions. And either abelian anyons versus non-abelian anyons. I think this can be kind of really interesting scientific object and potentially provide us rather emergent kind of particle that will truly give us that natures that we cannot find it out in the other natures, other than we can engineer in the 2D and immediately kind of spark a lot of excitement and interest in scientific communities. Not only it becomes a scientifically interesting, in fact, it has a technological relevance, and Klaus actually briefly mentioned about that, especially when it goes with the even denominator quantum states, for example, the 5 half states that appear in value function, right? Which actually is believed to have the non-abelian anyonic excitations in its particle nature. If we just kind of realize this one and somehow can manipulate it, there has been some of the theoretical the proposals as well as some first step of the experimental realization or attempt of the experimental realization, and just try to create those kind of non-abelian anion particle and just kind of manipulating them, especially grading them to create this so-called topologically protected the qubits of realization. And there's some nice kind of theoretical proposals out there. Indeed, if you can realize this in robust way, then we just demonstrated we can just kind of make this qubits out of it, especially topologically protected qubit, which in principle does not require the added fraction such that you can just get this number of the physical qubit is same as the number of the logical qubit can be realized. So if that is realized, I believe that is one of the very big leap in these technologies. But we can see that out of many years of the experimental efforts, we haven't yet get there. But I would say that we will see that some meaningful that the first steps that kind of stuff comes out in the community, and that's kind of something I want to share today. Especially that meaningful the progress has been made about 3 or 4 years ago. The first demonstration is let's starting from the before you even hit this non-abelian anion. Can we just kind of demonstrate the abelian anion? And it's just a chain series of the fractional quantum state, and whether we can demonstrate that indeed we just grading them and see whether the grading effect appears. And the first platform it was realized is Manfred's group, where that this is so-called the fabric cavities out of the quantum states can be built up, and the idea is that in this bulk quantum device, they just put down the this top gates where then you can deplete the electron underneath such that you can guide the electron to this path defined by the top gate. And you can make this narrow constrictions, what often we call this quantum point contact. The quantum states kind of flow through these edge states, and then in the ball quantum states. And by just controlling this the quantum point contact, you can just divide the electron, either go to the follow through the edges or just kind of jump onto the another edge of the side. So this the quantum point contact in a sense behave like the beam split. So having this two quantum point contact with this confined region, you can quickly see that this is basically the optical analogy of fabric cavity you can build up, where this quantum point contact actually acts like the beam splitter. And like the optical cavities, so once you just build up this one, you start to get this conductance measurement in the across this cavity, will give you this the oscillation as a function of magnetic field, as well as a function of the area changes, which is basically out of one. Now you just do this one experiments against the fractional quantum region, where now the current is carried by the edge state by the anyons, which is part of the the both fractional quantum states. And you will see that basically this anyonic the interference effect. In fact, that if you just throw that a couple of the anyons in the localized anyon in there, then this interfering anyon paths along the quantum states with these localized anyons in the center, basically you can see that there's kind of natural braiding operations can happen. And when that can happen, because of this anyonic braiding, we'll pick up this the particular phase that the anyon gives, especially if it's 1/3 is pi over 3. The phase will just kind of pick it up. If it is kind of circulating around, it's a kind of twice of the braiding. So you will get the 2 pi or 3 over this the phase will pick it up. And those kind of things will shows up as the phase jump whenever this anyon state is kind of the populating the ball. And indeed, this experiment beautifully demonstrated that this the around ball phase, ball oscillation, the interference pattern will break up in certain cases, and that the breaking point where the phase jump is basically computing, considering all this the electrostatics is about kind of the expected value of the 1/3 of the 2 pi over 3 of the phase shift in this complex. So this actually is one of the really interesting and meaningful steps in kind of showing the existence of the anyon in this system. About the same time, there's another experiment. It was a kind of French group that led by Fab. What's approaching is a little bit different. It's something that involved with the contacts and the sending the column. And this measurement is more like the so-called collide measurement. So in this case, they send this two anyonic particles from the one on the side, and at the quantum point contact, they collide and just kind of scatter it off. And using this kind of looking at the ensemble average of the situation is kind of the, I would say, anyonic version of the homomagnetic measurement. And just kind of looking at those kind of distribution post correlation, they could manage to just extract information about this anyon braiding phases out of this experience. Both of this experiment is beautifully kind of demonstrated that indeed the presence of the anyons and braiding phase of anyons can detect in the system. This experiment is now expanded into many different groups, or the same groups in the next stages. For example, here that multi-hadrons groups showing that again in this case it's not the fabric petal cavities, but this is the center cavities. But nevertheless, they actually detect kind of similar type of the physics in there, as well as now the non-fluorescent extended not on 1/3, and maybe for 2/5, and they were we are dealing with the 2 edge states. So all these things kind of shows a kind of suddenly burst of the progress has been made in this field in the past probably 4 years, or less than 4 years. What order I'm showing here is exactly is built on the values. Of course, the similar experiment can be done in graphene. And graphene, there is a bit of the more advantage as a kind of the person that worked for a long time in graphene. I would see there was some advantage in graphene in the following way. First of all, in graphene, that the quantified samples and verifications allows that the mobility of graphene sample is kind of approaching to the kind of very close to the best value estimate. I think mobility may not be good matrix. Here, the mean capacity of the electron is basically limited by the size of the sample, so that is very encouraging. But also, especially when you get into bilayer monocytic graphene, because of this accidental degeneracy of the availability of this accidental degeneracy of the wave function, and it's one wave function, especially in the zeros of the lambda orbital, you can rather easily get the even denominator states in the bilayer graphene. And it turns out that they are rather robust, and what you can see is not only 5 halves, you can get things out 3 halves to 7 halves into the electron side. If you go to the whole side, there's negative 1 half and negative 5 halves found to be also the even denominator state, non-J sequence of this conformal state is getting there, and the energy level is rather strong. And part of the reason is we can just be enough number of carriers and increase the magnetic field. We can get a fairly strong even denominator state, which actually can provide us one important the advantage over the gallium arsenide if you want to go to the non-homogeneous system. But also, the fabrication technology has been involved advanced in the past few years now. You can just kind of make this rather complicated step, but the important part here is graphene is encapsulated with boron nitride and the top and bottom graphite gates with all kind of this gate pattern. And in that regard, the state itself is completely consists of the Van der Waals system, where there are not many of the other the impurity states or the junks around in this system, which allows us to kind of make the discoveries relatively high quality. Right. The fabrication steps out of all this fabrication step, for example, this is now graphene based the fabric pedal quantum cavity. So you can faintly see that, but you can see that there is the cut here, and these cuts basically make all this top contact, and we just control all the top contact with the separate gate voltages. Graphene doesn't have the gap, therefore, that to have this depletion region, we have to rely on the sum of the quantum state, particularly equal zero quantum state, where the gap is large, and just kind of deplete the electrons there. And end of the day, then if you just put the different quantum state, you can guide this edge state through the whatever you design in this particular cases, right? So some of the older work a few years ago we demonstrated indeed, and as well as this Sisyphus with their friends also demonstrated a similar video. You can get this graphene quantum fabric cavities through the iron bomb dominated because there is the gate close by. They minimize this full interactions, and then you get this really nice iron bomb oscillation measure throughout this one to the integer. So at least we know that integer quantum this type of device worked really well a few years ago. Now this is a first generation device. Now over a few years we just improved the device fabrication technology even further. One of this issue of the first generation device is when you have this quantum point contact, quantum point contact, which actually is a very important elements of this device to split the electron beam into the two paths. There we don't have the really independent control because of this gate that usually the quantum pinching gate is being used as a zero quantum states there. So there is not much controllability we can get to control this transparency of quantum point contact. Usually it's controlled by the backgate, where that it's not independent control, but also device verification will be allowed of this some sort of resonance state near the quantum hole. So it's a little bit difficult to tune this both of the gates kind of separately. Now the new generation of devices that we just put this another overhang air bridge gates on the top of this quantum hole without any gate dielectric. Basically, it's air bridges. So that's the gate dielectric you can imagine. So we can have the direct control of this quantum contact with the two separate gates, which allows us that really high creation of high quality of the quantum contact also independently controlled by the gate voltages. So I think with this type of the device, we already have a better design that can be realized in gallium arsenide, where we just fully utilize that our channel is now can be exposed, and the additional the gate can be easily fabricated on the top of that. Okay, so I'm going to tell you that with this device, what can measure. So first thing that we can measure is basically we can revisit this integer quantum measurement, quantum interference measurement, and we can start kind of finding out. Right. So in this measurement, that I'm going to show you that we are changing the bulk, which can be also separated control by the gate. That we want to change the bulk, the filling fractions into the equal 2, 3, 4, and kind of higher numbers. And we are just kind of looking at this outer contour edges partition through the contour and just looking at their the oscillation, around home oscillation. What you're seeing here is as that bulk is assigned from equal 2, where you have this nice the so-called puzzle plot, magnetic field versus plunger gate, where the plunger gate is changing the area. So you see that to get into the fixed out-of-mode phase, basically diagonal should go in this way because multiple of this plunger gate with the magnetic field should be constant to keep the out-of-mode phase constant. Right? So we get this one. And what you see here is already as we increase bulk of the filling fraction such that we start calculating more of this edge states inside of this the interfering edges. We start to see that this nice out-of-mode phase will start to break up into the sum of the phase series, right? And that phase slip is kind of more regularly happening eventually, and the out-of-mode phase will start kind of double. So there's basically two important features we can see. The first one is as we just kind of increase this the bulk filling, out-of-mode phase actually double, and while that in between there we start to see that this kind of more of the phase slip happening. So our understanding of this, what is happening here is basically following. As we just kind of increase these bulk filling fractions, now edge states start, and initially we have this one edges, but the next edges start getting close. And eventually, that when we have this large bulk filling, some of the edge states is getting here and pushing close by, and eventually they will just hybridize kind of deeply. And basically, we have to kind of work with the one hybridize as kind of the part, which will give you just the phase doubling. In between, when this the edges getting close by, basically charging off this inner edges, which is isolated, that will just give you the space slip because of this. Whenever we just throw the charges in the inner edge states, there's spring charge should come from the outside by the Coulomb action. It will give you just this phase slip. One way you can see that is basically just compare the inner edges and the outer edge partitions. That if you see that whenever just we have these inner edge partitions, that then events that come with the outer edges really nice appears, and this is inner edge partitions. And if we just can go back to the previous one, and those kind of thing is related with the phase we are seeing here. All right. So the bottom line of this is basically when we have this cavities, and then we have this something inside, and like the inner edges or the localized state, whenever we just can put the charges there, basically our interference signal can pick up those kind of charge changes by just looking at the phase. So that's kind of very important information. Now, of course, the integer edge is a kind of already boring object, so we won't kind of move on to the expression. So same device, we just crank up the magnetic field now up to 12 Tesla, and that now that we do 1 and 2, but in between there are all this kind of fractions coming up. This particular device is a single layer Graphene device, so we don't have any even denominator states yet, but we can see that with a nice sequence of the series here. Yeah, I'm going to show you that data from the 1/3 and 4/3, which is the most kind of well-developed these fractions, and see what happens. So experiment is very similar. That basically we put this sample in the bulk, the 1/3 or 4/3 states, and just can partition the outer edges, which is the fractional edges. So the Anyon is flowing there, and we want to see that whether what type of this the interference pattern will get. So let me show you the 4/3 states first. So there, that basically is one integer, this one the Anyon edge is flowing there. The partition is that inner edges in there, right? So the experiment we did is basically we just try to kind of measure the interference, but the experiment, the first impression we had is the experiment is miserable there. We never get this really nice out-on-bone interface. So we just scratch our head and what is going on? Something's wrong here, right? And then the Tom was looking at that the kind of very noisy signal we had, very careful. They just kind of quickly find out there's interesting patterns in our noise that we get. So this is the data that everything is fixed. Magnetic field is fixed. your conjugate is fixed, your bulk is, everything is fixed, and just kind of it's a time sequence. So it's fluctuating. This is very noise data, but you start to notice that, hey, that is noise, but there is a kind of interesting kind of things can happen, right? There's only kind of 3 levels of noise. So it's kind of the telegraphic noise, but there is a 3 levels there, right? So for example, there is a 3 level that you can just kind of make it histograms. Okay, so somehow this state is a more kind of bubble, and that's the next one, this one. And no wonder we don't get this really nice the interference pattern because our signal is fluctuating over the time. So some of it, usually this is case that, oh, you have some bad fluctuator in your sample, it's the windy experiments, right? But then what we found is that we just kind of change that the conjugate, start kind of change the conjugate, fix everything's there. And then initially that is basically 3 point of this conductance values we have. But then sweeping this conjugate and just repeating this experiment and basically report where that we have the 3 levels, and then what is the distribution look like. That distribution start to follow this assignment sort of way in 3 different phases. And this the different color scale shows that what is the wave. So you can even follow this guy, it's beautifully following the sine wave. And the other one, more like this right description of this the 3 of the branches, basically each of the sinusoidal wave is exactly 2 pi over 3 for 120 degrees of phase separation, and basically the 3 phases. So natural wave that we can write down the signal without any interpretation is, well, this the conductance change is basically sum of the sinusoidal functions with the theta is changing by this linearly changing with the gate voltages around both phases, right? And then there's a phase shift is basically mode of the loop. So what is natural interpretation? Interpretation is then basically that somehow there is this fluctuator we have only give you 3 different states that give you that this is a set amount of this fluctuation. In fact, this is precisely what I've been expecting in the field sometimes. And there is some of the expectation that even dated back to the input of earlier in the 2000, that there is some consideration, what if that there's a localized states inside of the quantum system, and then if we just build up the interferometer, what is expected to happen is, of course, there's this phase shift is happening, and the reason the phase shift is happening is exactly the formula that I just approached you before. This is an around one phase, which can be controlled by the magnetic field or the conjugate, but also that there is an Anyon braiding phase that can happen, and this Anyon sitting inside of your quantum dot, as we just kind of change of the population of the localized state, will get this phase shift out of this conductance, and that is precisely what. In this experiment, actually now, we can not only change the conjugate and change the magnetic field and see what is that. So again, the Newton one, same device, we just can put into the bulk Newton one, and this is time sequence, basically is conjugation with the time sequence. You see that with time repeated, nothing is changing. So sorry, signal. In such a cases, when I start changing magnetic field, we get this beautiful pattern flow. So showing that indeed Newton one, we get this the quantum interference in here. The Arnold interference patterns can be made. In fact, this flow will give you the size of the dots, which is about 10.8 micrometer squared. If I just repeat the same experiments with the magnetic field changes, this is what is going to happen. Even before I just change the magnetic field, the fixed magnetic field, just kind of repeat it, I don't get any of this kind of regular signal. And that is clear because, well, you know that's basically what random jump words is kind of messing things around. In fact, this is the first result we get with the magnetic experiments that we thought kind of something screw. But again, if you just look at each of the traces is followed to the sine wave, but at some point it's a phase jump to another branch or phase jump to another branch. Basically, there is enough number of the phase jump between that is about 30 seconds of time frame. Will basically shift the distance jittering around, and that's why we make this type of pattern, which make us difficult to create this type of pattern flow. Right? But there is a way that we can just do that. The way that we can do that is at the fixed magnetic field, we can just basically do the same thing. At the fixed magnetic field, we'll just kind of go through that, make the histograms out of it, with the frontal, which frontal gate, we can get the histogram. We get these 3 branches we get, as I mentioned, right? Now, with this, we can start to change the magnetic field and create those kind of same parts of the histogram. And this is one. As we just kind of put down the magnetic field of 12 Tesla to the low magnetic field, we start to see that those kind of 3 branches will just kind of smoothly changing out. If you just follow through that, what is this phase of change of the magnetic field, which will give you that the area of this the interferometer, which is about again the similar area that we get in tissue, showing that indeed this expansion can work out. Right. So all these things shows that, in a sense, that the whatever switches we have in the system was in a sense illusions, but in this particular case, it actually comes as an experimental blessing. Because basically this work naturally allows us to kind of access the phase shift of this Anyon braiding phase. What is this nature of this fluctuation? One thing we can just do that is we can just change the temperature and ask what is going to happen. And when we change the temperature, of course, that the things that changes, first of all, this fluctuating amplitude increases. But also you can see that this the switching rate also got changed with the temperature. The first thing, this amplitude is more like related with the visibility of our interferometer. And what you see here is from the 20 millikelvin up to the 200 millikelvin, that is the visibility decreases exponentially, which actually is kind of usually thing happens in the quantum interferometry. So that's kind of something that we get. But the more interesting part is that this rate changes. It turns out rate is changing exponentially, or more stretching exponentially, right? And then obviously, what is the best formula? We can just go there. Basically, it's a variable range of increment of the address of the actual state of the formula. And this can you work it out and give us about this the time scale, the energy scale of the formula. So we believe that once all this kind of switches is nothing but very similar version of the localized states sitting inside of our interferometry that annual number is kind of populating. And of course, those kind of number of the site will just kind of give some distribution like this or the other quantum state. We can just kind of do the same analysis with the plateau, the length dependence. Plateau, along the plateau length, what you see is that this differential rate will changes the small to the large as you approach the edge of the plateau. What is the unexpected? The interesting part is if I just kind of look at the spectrum of this the fluctuation, the spectrum, especially low frequency spectrum, change it to this the 1 over f to the 1 of this the f squared. Inside of this the plateau region, we get more of the f squared type of this the fluctuation. As you approach this edge of this plateau, there is the 1 over f type of the fluctuation comes in. Tells us that indeed this is related with the whether we have the more of this single time scale of the fluctuation versus multiple time scale. So all of these things kind of the analogical that what has been studied into integer quantum pieces. Now, one can do kind of other things. For example, because we have now this time sequence of the fluctuation, one can, for example, analyze that. What is the, if I just can name this as 0, 1, 2, it doesn't matter, it basically is given the names of the different states. We can compute that joint probability density of this time correlation out of this one, and you can get this the time correlation and analyzing this type of this the probability correlation, one may be able to find out what is the nature of this. So all of these things actually shows that indeed getting this the interesting fluctuator, we can just explore the other window. Now, as I mentioned, this is the first time of this, a lot of the similar experiment is happening there. So while that this experiment is happening, there are kind of 2 other groups also shows somewhat related, but somewhat different the result based on graphene. This is Yuval group, shows that in this particular case, they use a bilayer graphene. And obviously, they're aiming for this non-abelian state. At least they are seeing that nice around home oscillation with the new for 1/3 of the fractions into this bilayer graphene device. So Andre Young's group's device also showing this single layer graphene component interferometry. They are seeing the very similar type of phase jumps around with some of the fluctuator. Their sample has a little bit small time scale of fluctuator, so they cannot make the statistical analysis of what they did, but getting it from the similar. So I'm sure that this field is rapidly progressing and there will see something. How many times?
7 minutes.
7 minutes, okay, good. I will just kind of use 3 more minutes for that. Even more exciting things. With very preliminary video for only 2 weeks. Let me show you that the motivation. So motivation comes from that when we post that papers about a month ago. Saka sent me email, as usual. And then actually unusual part is that email follow up with read this email as well. And they just pointed out, hey, you have to read my paper. Actually, I did before, but anyway, so. But the important, this paper was posted out last year and was a response of this non-classic experiment. I pointed out some interesting part. Basically, it's the whole point is basically, well, you know, that exchanges and then grading or the just kind of this the grading in a sense that I just or the grading as a the fabricator interferometer. In fact, is a different. In fact, that exchange is twice of the exchange is one grading in this way. But actually, this they actually claim that you cannot call this is grading because as it defined in the old times, the grading is just kind of same as exchange. You should call this is double grading. Okay, so that's a nomenclature. So that's okay. But there's one important point that this writing is saying. One is basically exchanging phase and grading phase, or the double grading phase, like we're measuring, that's the effect of the two of the differences. And the effect of the two differences, but experimentally, you only just detect this one so far, right? Has the ambiguity because of this modular two findings. So basically, with this one, there's always a factor of the plus, the factor of the plus the sign of this ambiguity. Onto getting to the specify these exchange states. In other words, you cannot just do this experiment and then you cannot distinguish electron versus boson. Right. That's basically a situation. And if you go to the Anyon, that I can claim that it's a basically we can see the 2 pi of the 3 of the phase shift into the double grading experiments, but then I cannot specify exchange statistics. Up to the, I can only specify the exchange statistics up to the side. So that's basically the problem. Interesting enough, actually, this paper followed a few weeks ago that there is the papers that were being posted by Peterson. And basically, there's a way that you can mitigate these issues by just putting that quantum dot into one of these quantum point contact. The idea of this experiment, this proposal is by just putting the quantum dot, there's a way that you can just implement this direct access of the exchange statistics. My quick reading of this paper is that basically when you have the no anyons sitting in this quantum dot, you get always a direct tunnelings there. Then you get the, as usual, the double grading the sequences. However, once you just fill this the quantum dots with anyon, their following sequence is possible. That this anyon comes out and new anyon is coming in. They furnish this one, and that allows only kind of half of the grading operation can be detected by the experiment. Therefore, just looking at this experiment with this, where when this quantum dot is populated and unpopulated by the anyon, comparing these two, then you should be able to get this the phase information of this the exchange grading sequence or the real exchange grading sequences. Turns out this experiment can be realized in current cases because we cannot put the quantum dot yet into the quantum point content. But because we have the gate, we can just tune this gate and hope for there is an accidental quantum dot may form at some point into the gate voltages. Indeed, if you just look at very carefully, sorry that this is a really late last night, and all of you can see that it's not just pretty, but anyway, to show you how they progress is being. So this is quantum point contact, the measurement. We can just control with this quantum, the gate voltages. We can see that this is a 1/3 gate, the fielding. Then, if this is a fully opens up, this one goes up to the 1/3 of E squared H. But then, as we change this one, at some point we start to see all these resonances, right? But this resonances are rather sharp. And if you just look at the getting to the one of the sum of this resonance region, and now change the source drain bias voltage like a quantum dot experiment, you can see that there is kind of some sort of Coulomb blockade type of the peaks appears. Source drain bias voltage is quantum. So what we can do that is basically if this is indeed kind of quantum blockade, Coulomb blockade dot, and Anyon is basically Anyon number is changing across this the resonance peaks. We can just kind of compare my the quantum the oscillation across this two dots. We should be able to see that whether indeed the phase shift is happening, and that's basically what it is. So this is conductance now that using this cavity, and this point of the gate voltage, this point of the gate voltage, you see that there's a 3 branches comes around. We didn't color it yet. We can do that. But if you carefully look at there, that there's a phase shift between this point and the shift across this the resonance peak. Indeed, kind of confirming that what Kiberson is proposing, that across this one we can just specify the sign of this landing rate. So that's kind of the ongoing news. What you're seeing here is clearly that the field are making kind of really progress here. We start kind of showing that we can just make this kind of braiding demonstration using the fluctuator. We can start kind of install this the quantum dot, although it's excellently developed. But the next step is, well, can we actually make this really artificial quantum dot wherever we want to design? Indeed, with the graphene experiments, there's a lot of the open device geometry in and installing those kind of the gate structures in principle possible, and that's kind of some things that are going on. And furthermore, moving into this even in many more states where the bilayer graphene provides you very strong the evidence of this even in state with the large gap. We believe that we are getting close with the real and doing this expansion into the non-observable systems. Thank you very much.
Okay, we have time for a couple quick questions. Yeah, Abraham.
Thank you for an amazing talk. So I have a few questions actually, but the trivial one would be you're braiding these Anyon's excitations on the edge state. How should I think of the edge state in terms of, you know, compressible, incompressible excitation above the, you know, all that?
Exactly.
Yeah. Because in the bulk, I understand maybe you can have 1, 2, 3, you know, Anyons sitting there in some puddle, but on the edge, like how exactly do I think about it?
This is a continuing discussion after 2 years ago that we had this. I think I would say we can refer to the later kind of data, but kind of when you get into the really close to equilibrium, we are applying a very small bias. It's not a breakdown of more cases. There are the edge state pictures with the lambda beautiful formulas works, and that's been basically one way you can see that is even in integer nice the amount of state pictures. So all there that we can just kind of rely on the lambda. Now, in my opinion.
No, I'm fine.
Okay, well.
Do I have to understand literally that you have 1, 2, 3, or you have big number inside of localized state?
Yeah.
And so that's a macroscopic number, and then Efrash-Klowski may be applied, because if it's 1, 2, 3, it's not clear.
Yeah, that's right. So we don't know that how many are there. So that's kind of the question. So there's not an easy way that we can see that, but there may be many, but how many is it? We don't know. So there is an interesting trend I can point it out. So we did that. I'm sure we know that as we approach the edge of the plateau, there are many. But the reason is basically the spectrum of this the random kind of noise start to show as a monogram. type of this spectrum. Okay. Make it transient. So which means that there's multiple time scales get involved there, meaning that there are multiple sites, right? So as we just getting to the within the plateau, we are getting to the spectrum that is the 1 web square. So that doesn't necessarily tells me that how many is there. There maybe it's one single time scale, but it doesn't necessarily tells me what is time scale. So unfortunately, at that point that we cannot say that it's more than 3, but it's a how we talk about 10 with the same type of time scale, or it's just a 3. We don't.
One more maybe. I think Klaus had his hand up first, if you don't know.
Broad is a secret for very good graphene samples, but you always produce a moray or something like that. Do you have to take care or worry about some other gaps?
Yes, I think of course the twistings and the aligning bolonite I give you another freedom. But in this particular experiment, we want to get into the vanilla plane quantum hole, or fractional quantum hole. We don't want to kind of mess by the bolonite, right? So we are in fact to try to carefully disalign with the bolonite, right? Such that water physics is not needed there. But certainly, I think eventually getting this more tied with the water physics is also very interesting topic, because there has been some report that there's a kind of fractional challenge later type of physics can be realized with water aligned with graphene with the magnetic field. But at this point, we are just we want to kind of get the vanilla plane quantum hole, which means that no water physics.
Okay, raise itching for one short.
Yeah, I just did this sort of unrelated. This early part of your talk was the H/2E stuff.
Yeah.
That you see, H/2E flux quantum that you see.
Yeah.
And it was 4. Does that extend to lower? I mean, Heiblum has it down to 5 halves, and we got it below 5 halves in our quantum dot experiments. I'm just, fascinated by, what are they? How does it work in graphene compared to gallium?
Yeah. So I think So let's see. So we start to see that from the 4 or 5 type of things that we did see that kind of general things happen. Especially once you kind of push this the closest edges very close by, basically we don't necessarily see any of the changes there. So it's basically kind of fixed with this frequency doubling and fixing.
You don't see it extending down to numbers 2. It's not. I guess it's very different from Heiblum.
That's right. It's a different. There's a kind of clear difference between this type of graphene experiment with what has been seen by us. Right. And the susceptible groups result even show that they are seeing that sometimes even frequency triply, meaning that maybe they are claiming that the 3 edges can be a bunch of scale type of things. So potentially that what has been seen in gallium arsenide frequency doubling might be different origins that what they're seeing. That's kind of it.
Okay, well, let's end there. Thank you again.
Thank you.
Well done. Okay, go ahead. I'll give you the 10-minute warning.
10 minutes?
I'll warn you when you've got 10 minutes left.
Good morning, everyone. It's my great pleasure and honor to join this wonderful company. My congratulations to Boris, who is here.
Probably in the restroom, but he'll come back.
Okay. So, then let me start. So the title of my talk is "What Hall Stripes Surprising Encounter." So the work was done in collaboration with my student, Julian Bell. Samples came from Princeton University. It's working. Right. That's the let's use my. All right, so I will my first slide is traditionally about quantum Hall. All I need to remind you about is that the important parameter is the filling factor, which is the number of fields, lambda levels. And Boris is not here yet. My focus is on his seminal work on charge density wave, also known as quantum Hall stripes. So all three authors are supposed to be here in the audience. Alex Polakov, Misha Fogler, and well, Boris is probably will come back. Right, so why do we have stripes? In the simple picture, you need to think about interaction between two ring-like wave functions and think about the overlap. So the interaction potential looks like a box, and it becomes energetically there are multiple electrons to cluster in order to avoid other electrons. So the result, when some down levels usually have full, one expects stripe-like pattern to move away from hard filling. There are bigger crystals of many electrons per cells known as bubble fills. And one thing I wanted probably to mention that no broken stability states, such as these, are expected in the lowest 1 hour. Okay, so the predictions by Boris and company has been verified in experiments by Louis Du and Jim Eisenstein. And they manifest themselves as strong anisotropy in transfer. So if you measure the resistance along one crystal axis, 110, you'll have at 9 half, 11 half, 17 half, very small values. In the orthogonal direction, you get strong peaks. So one question was why are stripes aligned along certain crystal axis, which is supposed to be due to some native symmetry breaking, but many scenarios have been proposed, but to my knowledge, none of this has been proven as a dominant source. Okay, so what has been done with stripes, probably the very first experiment after the original discovery was application of in-plane magnetic field, which will be relevant to my talk. And the theory basically predicts that the anisotropy energy which is induced by in-plane field is kind of isotropic. So if you start with some native symmetry breaking energy, right here apply magnetic field along one direction, eventually stripes through the area, which was indeed observed. So easy and hard resistances switch with one another. If you apply magnetic field perpendicular to the native stripes, then nothing is going to change. Basically, they're going to remain. So the conclusion of this theoretical work in the initial experiments was that stripes prefer to orient perpendicular to the in-plane magnetic field. So we have studied same effect. We started looking at stripe phases roughly 10 years ago, and we immediately found that the story is not that simple. So we have found that there are more reorientations than expected. You start at 0 degrees, you see red stripes aligned along y-axis, vertical stripes. Then we see reorientation, stripes being perpendicular to in-plane field. That was seen before, but if you increase the in-plane field even further, stripes eventually become parallel, right? If you do apply magnetic field in the opposite axis, they also orient parallel to in-plane. So the anisotropy energy, which can be related to the anisotropy, looks something like this. You have native energy over here, two reorientations when the magnetic field applied along y-axis, and one reorientation when you apply in orthogonal. And if you look at spin dependence, the story is kind of gets more complicated. So at 9 half, you can easily get both reorientations right away. At 11 half, it takes a little bit higher values of in-plane field. 16 half is again kind of small, and so on and so forth. So there appears to be two mechanisms. One is insensitive to spin on Aldau level index, another one is sensitive to both. Okay, this brings me to the main part of my talk. And what I wanted to show you is that we have recently found stripe phase, which looks like this. So it's third and 7/3 mark here is a filling factor. So we are around filling factor by half. And we see that there is a very strong isotropic phase here in close to 7. Right, so I probably want to tell you a little bit about the samples. So let me remind you about the concept of composite fermions. So you take electrons attached to vortices, you end up with weakly interacting particles, which can be used to interpret fractional quantum Hall effect of electrons in terms of integer quantum Hall effect of these composite fermions. So there are several families of those 2-flux quantum composite fermions live around filling factor 1/2, 3/2. Then you can have 4-flux quanta and so on and so forth. So the state-of-the-art data, transfer data from 2002, look like this. So here you can see filling factor 1/2 marked in pink, and those fractional states continue up to 1019, 1021. Around 1/4, they go up to 6. Lambda level of composite fermion, there is also a fractional quantum Hall effect at 4/11, which is currently understood in terms of interaction of a fractional quantum Hall effect of composite fermions. So what we are going to use in our study is a new generation of gallium arsenide quantum wells. So a few years ago, there was a breakthrough in mobility. Mobility roughly doubled at lower electron density, and that's where we are going to work. So some details about our samples, some specifics. So we have here I'm using 4 samples. So the second column shows the width of the quantum well. This column shows the density. So density ranges from 1 to 1.8, and mobility is pretty high. It's around 40-50 million. All our samples are electron monolayers. So here is a calculated density profile in our quantum well. So there is no second subband populated whatsoever. In this sense, our quantum wells are not white. Usually when people speak about white quantum wells, the second subband is popular. And here's how the data from this iteration sample look like. This is just standard transfer trace. One thing I wanted to mention that at 1/2 we get to much higher fractions up to 18 and 17, as opposed to 9 and 10. If you go to 4-flux composite fermions, around 1/4, we go instead of 6 up to 9. So the quality is pretty good. We have also some signatures of even denominator states, very strong for 11, so on and so forth. So the quality is pretty decent. Now, what we are going to do, we are going to apply in plane magnetic field in addition to perpendicular. We are going to tilt our samples. So why do that? So I already showed you that magnetic field, when applied in the plane, can provide symmetry breaking to real stripes. It can also transform 5 atoms out of fractional quantum Hall states in stripe phases. So basically create some stripes where they don't usually present. Of course, you can think about Landau crossings due to the multiple subbands or electron spin. The magnetic field can also tune electron distribution, which leads to transformation of electron monolayer into bilayer. Tell you about that later. So why we got interested in that? So basically, about 10, 12 years ago, we were left with non-working system in Florida, and we had nothing else to do as to tilt our sample in field. So we went to very high tilt angles, around 87, 18, 88 degrees, and looked at what happens to shooting of the atlas. And what we saw is that there are multiple coincidences, multiple level crossings, and at the end of the day, we came up. We came up with this kind of phase diagram which plots their filling factor as a function of inverse cosine of the tilt angle. And the experimental points marks the incidences which we have observed up to like 5. But what's interesting about this is that if you look at the lowest corner, you see that when the field factor becomes very small, you don't need to tilt a lot if these traces, of course, are correct. So what's happening? We were able to explain our data by looking at the change of the effective mass, which happens with the finite thickness of our system. Right. So here we use parabolic distortion model to kind of map our data. So our motivation was actually to look at what we can see at lower field factors in the fractional quantum Hall effect regime on the in-plane field. And I'm now switching to our data. So here's basically, let me explain. So I'm going to plot. At the bottom, you will see 2 resistances measured along 2 orthogonal directions, RXX and RYY. And this is, of course, is fault trace. So the range of field factors I'm going to focus on is between 3 and 2. So here you have 5 paths. And at this particular angles, 73.5 degrees, we don't see much. We see that our transport is more or less isotropic, and we have 2 fractional quantum Hall states that create serve themselves. Nothing else. Now, if I tilt the sample 1.8 degrees from that end, I'm going to 75.2. Again, I see roughly isotropic transport, but I see the appearance of 2 new fractional quantum Hall states, 12 fifths and 13 fifths. And I probably want to remind you that these particular states are very difficult to observe, are without in plane fields. They're usually very fragile, very weak. You need to go to much lower temperatures. So what is happening in between these 2 states? So looking at the range of just 1.8 degrees, we can. So let me walk you through. So the bottom plot over here shows the data I showed you. That's 73 something degrees. And I'm going to increase the tilt angle in very small steps. I will tell you what those steps are a little bit later. So upon small tilt, I see that in the middle panel, there is a very big strike phase appears where you also have integer quantum Hall effect in factor 2. You have some re-entropy integer quantum Hall effect, which might be a signature of bubble phase. But once I tilt a little bit more, I have very strong anisotropy. So one trace is goes basically to 0. In another case, I have about 5 kilos. You still see a 7/3 fractional quantum Hall state next to it. And now I'm just will keep tilting. So the strongest phase is observed at this angle. It's roughly around 7/3. There is no fractional quantum Hall effect anymore. And then it continues to move towards 5 path here, but it gets weaker. And at the end, it virtually disappears. And at the time it disappears, you get those new fractional quantum Hall states, which are not present at lower tilt end. So here's basically the same data I showed you, but they are zoomed in, so you can see more details, what's going on. Actually, plotted this way, you can see that there is still small anisotropy around 5 path over here. This was 22 nines minimum. So what is going on? And now, actually, this is again same data with the log scale and with the angles marked 73.5 up to 75.3. So that's was from one sample. So we decided to check other samples with different densities. So here is sample number 4. And basically what we see is very similar story. So here we start from A to F, so we're going from top to bottom. So very weak anisotropy at 5 half, but it's always present and nothing happens to it. But otherwise, the data are isotropic. Then we have strike phase showing up next to field factor 2. Then it moves in, becomes stronger. The strongest are again around 7/3. But here we also kind of have it rather strong around 5 And just for completeness, I'll show you some temperature dependence or conventional stripes predicted by Boris and observed with high Landau levels. Usually disappear at around 100, 150 milli. But here we are in very strong and plane magnetic field, or it's not probably not surprising that our stripe dies only at around 0.3 Kelvin. But here are the temperature data. And for whatever reason, the minimum, the easy direction stays easy up to the highest temperature. And on the right, I'm showing the resistance at the peak as a function temperature. And it gives the temperature or energy scale of around 2. So what we have found so far, we have found that, well, I didn't tell you that, but we see that the easy anisotropy axis, the direction in which we have small resistance, is along in plane magnetic field, which basically is the same as that for the conventional stripes, as provided the field is strong enough. Well, now this field is strong. Another thing is that the width of the stripe face in terms of the filling factor, even though it moves, it's not fixed, stays roughly constant around 0.2, which is actually the same as for Boris's stripes in high Landau levels. So I already mentioned that it is strongest at 7/3 or whatever, that while the conventional stripes are in half field Landau levels. So what might be better? So if plane magnetic field can do two things, as I mentioned. Of course, you can expect the crossing of two Landau levels. In this case, it would be the lowest Landau level with spin down and the first excited Landau level with spin up. And you can also think about monolayer to bilayer transition or increase of the effective mass. But those are going to be related. So in Klaus's group, not so long ago, 2018, there was similar experiment done on zinc oxide. Again, focusing around filling factor 5/2, same range. And what you can see here is that 5/2 are initially quantized and become compressible, becomes quantized again. But once the levels have crossed one another, there is also an isotropic phase, very similar to what we see. And again, it's not centered at 5/2, it's kind of shifted between 5/2 and 7. Very simple. What's different is that the easy axis of this phase is perpendicular to in plane fields, which is opposite to what we see. Now, let me show you the data from the lowest density sample, which is at 110 to 11. And this sample, when we studied it, it looks somewhat different. So I probably should have mentioned that when we observe those states at 12/2 and 12/5 and 13/5, they can be easily understood as being due to crossing. So we are ending up in the lowest Landau level, which allows naturally for this stage to form, if it is a level. But studying sample 1 and sample 8, we have found that those states at 12/5 and 13/5 are already present before we start seeing the stripe phase. Otherwise, everything looks very different, but we do have those fragile states clearly observed, clearly developed before development of this stripe. They still get stronger then, but they are present from the very beginning. So this is not consistent with level crossing. This, we should think that level crossing has already occurred. So, what about the bilayers? Can we think about that our system, upon application of a plane field, eventually splits into two independent layers? So here are the theoretical calculations by Ludwig Schmutzke, showing that there's a, here you can see the evolution of the Energy dispersions, you start with two parabolas. In this case, the second subband is occupied, but eventually once you lie in plane field, eventually it will split and thermic contours will look like this. So at the very point where the splitting takes place, when you have these two piecing thermic X, the effective mass is expected to be divergent, which naturally can lead to strong anisotropy in transit. And upon further tilting, the mass actually goes back to rather normal values, while it's still enhanced by a factor of 2. So here it should be looking at basically 2 electron wavelengths. So do we have any evidence? Well, let me remind you that when you have either a wide quantum well or you have double well, you can expect multi-component fractional quantum Hall states, such as 11/5, 19/5, 29/35, and so on. And those states, those fractions, will look quite complicated, are nothing more than just a sum of 2 chain fractions. Okay, and here's a table showing 11/15. It's simply the sum of 1/3 and 2/5. You have 1/3 in one layer and 2/5 in another. So you can do 2/3 and 3/5 to get 19/15, and so on and so forth. So what we have indeed found that we have many more. With 2-component fractional quantum Hall states. So 19/15 was observed previously, but we can go higher, see 41/35, and they extend all the way up to actually 12/11. Here there was a constellation of high feeding factors, but 1/99 is there. On the other side of the feeding factor 1, we also see plenty of those states up to 106.7. Now, if we apply Planck field, increase the plane magnetic field, eventually those layers should become independent. They shouldn't talk to each other anymore. And tilting to 87 degrees, but now looking at the quantum Hall states, we indeed observe that quantum Hall effects at 4 integer feeding factor completely disappear. We only have 2. Well, here you don't see 2, but you see 4. There is no 5, there is no 3. You do see 3 or 6. 7 is kind of hanging there, but well, the dependence on the feeding factor here is simply because we are working at a fixed angle. So once we move to high feeding factors, the plane field gets smaller and smaller. So here, the layers are still kind of not independent. So in summary, so we found there in the tropic strike phase near 7 so it is likely of 2-component origins, maybe 2 spins or 2 layers. We still need to figure out. Many new 2-component fractional quantum states were found along the way. But the message is that in plane magnetic field can be used as a tool to induce new quantum phases by modifying interactions, making them isotropic. We can also have a collapse of cyclotron splitting due to divergent effective mass, continuously tune interlayer coupling at the end. And finally, I wanted probably to spend a few minutes telling a little bit about what we have been working with Boris over the last 5 years or so. So it was my pleasure to collaborate. One of the first papers was about trying to understand what determines the anisotropy of conventional quantum Hall strike phases. And the calculations made by Boris and his students have shown that it is basically determined by the mobility. And there is a parameter which tells you about the relative contribution to mobility from scatterers in the quantum layer, well as scatterers in the base. And we were able to map data from 3 samples as a function of this parameter, and we observed reasonable dependence over at least 1 order of magnitude. So that was our first thing. Then, second story, which we worked on, is known as hidden quantum Hall stripes. The stripes don't always reveal themselves as transport anisotropy, but under certain conditions, when the mobility of scattering is dominated by short-range impurities such as aluminum gallium arsenide quantum well, it was shown that there is a region or range of filling factors between the conventional quantum Hall stripes where you do see anisotropy and so-called Zawadzki's tetrahedral Zawadzki's tetrahedral phase where you expect the 1 over nu decay of the resistance at the maximum, basically due to changing the density of states. But here there is a range where resistance is isotropic and it doesn't depend on the plane field on filling factor as well. Right? So there was a phase diagram constructed and basically everything was well understood. So one advantage of this phenomena, it has a potential to be found in dirty systems where the scattering is short range. And we also worked on understanding what limits the mobility in modern gallium arsenide quantum wells, including their latest generation, that's samples we've been working on in our experiments. So again, we were able to find how the mobility should depend on density, it's the experimental data, and basically the conclusion was that it's not remote impurities which limit the mobility, as one might have thought, but it is rather interface roughness or alloy dissolvers. And before that, there was another, that was our very first paper, for instance, that's, I believe, is very, very important because if you look at the traditional expressions for mobility and try to calculate it based on where your scatterers are, remote donors, and what is the spacer, you'll get the number, which is at most 10 million. But we all know that samples with 30, 40 million mobility do exist. So Boris has shown that it is a screening in the docking layer, which actually eliminates the scattering from remote ionizing. So with this, I want to thank you everyone for your attention and the data.
Big questions, please. Yeah.
When you have a in the parallel field where you think that you might get splitting, is it possible to get exotonic effects like in Eisenstein's double layers?
I believe it can. Filling factor 1 believes this is one half step.
And can you measure it? Do you have access to top and bottom?
No, here you cannot do double well for it complex. But very so we do have some but I didn't show you here, but there is also state next to we have very well quantized three couple well, which is the same origin. And there are some unbalanced states which interlay a couple. When electrons get not only flux wanted from its own layer, but also from. Yeah, there is evidence. I did not.
You mentioned there's an anisotropic state in the filling around the filling 7/3.
Yeah, that's where it gets the strongest.
Yeah. It's not if the possibility that the single layer can be split to bilayers it exists. Mm-hmm. It's not necessary that this anisotropic state is the charge density wave state, because if you have an anisotropic mass, then the resistivity should be expected to be anisotropic.
Okay, so it's one issue is this. Of course, we are thinking about those lines, but the direction of the anisotropic axis is predicted to be opposite. Probably you're familiar with the paper by Zudov about transition of I half to stripe phase. as a function of mass and isotope. But it is the opposite. And also there is an experiment by Mansour Shagan in aluminum arsenide where you have naturally isotropic mass. If you depopulate one valley, you end up with mass and isotopic factor of 5.
Yeah.
And they do see stripe phase next to 3.5 in that case. Again, the direction is consistent with Soderman's populations, but we have here the opposite. I don't know. Just telling you what happened.
Any other questions? I have maybe a very basic question. So when you talk about the possibility there's 2-component quantum Hall state with different flow effect. This doesn't involve like different sublevels or it does. Like you said at the beginning that your quantum wells are very narrow, so there's only one sublevel problem.
Right.
But when you tilt, is there a possibility that you're involving 2 different sublevels or not? Like, you definitely always one sublevels.
You mean sublevels, electrical installation? Yeah.
In the Z direction, yeah. Z
No, that's supposed to go away even double. So what is happening? You can think about physical separation. And that probably can be in classic electron stars. You get right movers and left movers. The plane field is going to basically act as classical Hall horoscopes, going to separate it. And once they're separated,
there's not separation in the Z direction.
with separation in the Z direction.
But without involving different quantized sublevels?
No, it's yeah. So the theory by Schmutzker ends up with those levels to be degenerate. That's probably what we see at the very end, or when we lose all denominator functions. But in between this multitude of 2-component states, they're all in balance. Didn't mention balance states, of course. Six fields which can be plus 3. It's there. There are many imbalances, which means that there are 2 levels which are not together. But feelings in those layers are big.
Okay, any last questions? Well, now let's adjourn for lunch. We're back here at 2 o'clock. Lunch is on your own, so one clicks to go together.
You can leave your belongings here, the room will be locked.
Sure, you're good. Whatever document.
There were too many maggots in the room at the time.
I know Japanese came 74. I think you never paid the what lowers.
I think we can say such. The maybe side is maybe true. But not probably.
Uneventful, just those you can support.
I don't know. Certainly it's charged. Yes, yeah.
I heard you had an unusually warm winter.
I paid like $600 for the stove. Take on price.
Yeah.
Yeah, living in Ohio, I kind of miss the Minnesota winter a little bit. I always root for snow and it only comes for 2 days at a time. Which is quite- It's actually harder. Well, it's very inconsistent. The winter is kind of going above. Snow comes above this thing.
Yeah, well, so that's a very. So I think the concentration is.
Yeah, I feel like it's bad behavior. Well, my status is.
Whether that is.
Have you been in Florida?
Yes.
Also.
Yeah, we started in January. So we.
It's weird. This is in Tampa.
And it's south, even more south, it's 4-hour drive from Planck.
Oh, okay. So how do you like it so far?
So far, so good. We haven't talked for December, so we don't know how. Yeah, I kind of missed the cold here, so I think it's too hot there, so we might get some cool weather here.
Yeah, okay. Yeah, so that's why that I think we don't have to view.
One of my everybody's one PhD is from last year, even to
So.
some Georgia Tech, not Florida.
Yeah.
There, I recently took the advantage of from what we're driving from.
If I take your case, what is your case?
And some of the unlettered. It was, so we take multiple things. A lot of kids bring
Sounds like
most of them.
yeah, it's probably about.
Yes, almost, yeah, I graduated in 2022, I thought that was the year where it started.
Yeah, I have technically I started after. In 2000.
I knew we're gonna start on.
And our card said, please, very good. We should take
You want
it.
to go to
I
RPC?
remember that message.
It's small, but it's pretty.
Yeah,
good.
Have you already like you know put some you don't have a lot of or you know looking at
We're
it.
still.
Much less nice. But
Yeah, we're.
Take some time. I really pull out a year before I find like a good way to buy. So some sort of research.
If you focus on.
Reasonably close, 15 minutes drive. That's right near the temple. Not far. And these go around the same.
Yeah. It is.
So you know the Minnesota State Fair?
Yeah,
around that
I
area.
actually live in the CTC.
But that's all. So Minnesota.
That's always up here, that many things.
It gets
Eventually, that it's a very.
many cars parking.
Yeah, I don't know.
It's not even that powerful for kids. I don't know who are those people who just come from all over the place.
Actually, it was fun for me as a.
Okay, yeah. First time is fun, but it's not that unique, right? Sell pizza, sell hot dog, sunrise. That seems really fun. You can find that in everything. I don't know why people drive hours to come to.
Unfavorably.
So what my kids started to know most is
In contrast.
you heard the Wisconsin Bears, the water parks, about 3 hours. So we go there every summer. Because it's one of the cheap vacations.
Very
Yes.
Oh, yeah, we.
Yeah, that's.
So maybe you stay here.
So, you guys want to get lunch?
You taking him for lunch?
I have taken Philip to his favorite place. He went to when he come here for the
Oh, what's
for
that?
the
House?
no, not the house. It's a Chinese place.
Мы смотрели.
So Philip was going to the I remember you liked one of the Chinese restaurant when you came.
That was fast one.
It's a tea house.
This one here, yeah, close, almost as good as the one in Boston, yeah, not quite, yeah, so not tea house, not tea house. Tea house is tea house become worse, like in the past few years, but this place become better, so now it's the best place in town.
Okay, guys.
Anyway, do you mind if I follow you?
Let's go together, yeah. Chinese food is better. We can speak around
Yeah.
table.
I'm not joining.
And I'll just join.
Yeah. It's good. Yeah.
The more the merrier.
Yeah,
Yes,
that's-
you know, because we order more.
Yeah, that's right.
I remember you liked it, when you came here for the one plate, yes. Now it got better.
We're having Chinese food if you'd like to join.
Is it allowed to go to Chinese food? Yes. Not forbidden, Eddie.
I think that we can.
Yeah, you can choose here.
I come from that part of China, so.
Okay.
Я чувствую.
Я понимаю аргумент, банкет, но
Кафе тогда, ведь там суп дают. Ну там дают что-то. Ну вот туда где будет. Ну пойдемте, какой же ты хочешь пойти? Пойдемте, я вас поведу. Пойдемте суп поедим, кто будет суп?
Я посмотрел телевизор, как у вас.
Саш, всем вкусно. Дальше становится так больше. Сашка, не огорчайся. Все политиков